Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep story of when rain first fell on Earth. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, Earth spins in silence. No rain has ever fallen here. The planet's surface glows orange and red, a continuous ocean of molten rock stretching from pole to pole. Magma flows like slow rivers across a world that knows only heat and stone. Above this liquid landscape, the atmosphere churns with water vapor so thick it could drown a mountain, yet not a single drop touches ground. The young sun burns with unstable fury, sending waves of radiation across the inner solar system. Solar winds strip away the lighter elements from planetary atmospheres, but Earth's gravity holds tight to its envelope of steam. The planet absorbs this solar energy, adding to the heat already trapped within its molten core. Surface temperatures reach 1200 degrees Celsius, hot enough to melt copper, hot enough to turn limestone to vapor. In this inferno, water exists only as steam, invisible and patient, waiting for a world cool enough to hold it. Every molecule of water vapor that will one day form the first rainstorm already drifts through this superheated air. Some arrived aboard comets from the outer solar system. Ice transformed to steam in the heat of atmospheric entry. Others emerged from the planet's interior, released through volcanic outgassing as hydrogen and oxygen combined in the crushing depths. These water molecules tumble and spin through the dense atmosphere, occasionally colliding, briefly clustering, then separating again in the restless thermal currents. Sulfur dioxide and carbon dioxide mix with the water vapor, creating an atmosphere so dense that sunlight barely penetrates to the surface. The atmospheric pressure reaches levels that would crush any future life form, instantly perhaps 60 times denser than the air that will one day nurture forests. The sky glows a perpetual orange-brown, neither day nor night distinguishable in the eternal twilight. Volcanic eruptions puncture the molten surface like planetary breathing, releasing more steam into air already saturated beyond measure. The chemistry of this early atmosphere defies simple classification. Scientists estimate that water vapor comprises perhaps 60% of the atmospheric mass, but the exact composition remains one of geology's quiet mysteries. Computer models struggle to recreate the precise conditions when pressure, temperature, and chemical interactions push beyond what any earthly laboratory can replicate. Only took 4 billion years for this steam to find somewhere to go. Beneath the choking atmosphere, the molten surface writhes and flows in patterns that follow no familiar logic. Massive convection cells carry heat from the planet's interior to the surface, creating currents in the liquid rock that dwarf any future ocean circulation. These magma currents move at the pace of cooling stone centimeters per year, perhaps in the faster flows. What appears from space as a glowing, uniform sphere actually seethes with hidden complexity. Temperature differentials creating zones where the magma flows slightly cooler, slightly thinner. The planet rotates faster in this epoch, spinning through each day in perhaps 6 hours rather than 24. This rapid rotation creates fierce atmospheric dynamics, stirring the dense steam into circulation patterns that span continents. Coriolis forces twist the vapor into spiraling systems that have no comparison in Earth's later weather patterns. These protostorms carry no rain, produce no lightning, cast no shadows. They exist purely as movements in the invisible water that surrounds this molten world. Tidal forces from the nearby moon, still close enough to loom enormous in the sky, stretch and compress both the liquid rock surface and the dense atmosphere above it. These tidal bulges create rhythmic temperature variations as different regions move closer to and farther from the moon's gravitational influence. The result is a kind of planetary breathing, a slow expansion and contraction that affects every water molecule drifting in the superheated air. Sometimes, in the slightly cooler regions of the upper atmosphere, water molecules begin to cluster together into the earliest formations that might be called droplets. These proto-raindrops form and dissolve in microseconds, never growing large enough to begin falling before the thermal energy tears them apart again. The physics of droplet formation in such extreme conditions remains poorly understood. Laboratory experiments can approximate the pressure and temperature, but not the complex chemical interactions with volcanic gases and solar radiation. The silence here is absolute in ways that will never exist again on Earth. No wind through trees, no waves against shore, no rain drumming on stone. Even the volcanic eruptions produce no sound that travels through this thick atmosphere. The density and chemical composition absorb acoustic waves before they can propagate more than a few meters. Only the deep, inaudible rumble of a world still forming. Vibrations that travel through solid rock rather than air suggests the titanic forces reshaping the planet's interior. Somewhere in this steaming darkness, the ingredients for every future rainstorm drift and swirl molecules of hydrogen and oxygen bound together in precise arrangements, circling endlessly through superheated air above a planet that cannot yet receive them. Each water molecule carries within its structure the potential for rivers, for snow, for morning dew on grass that will not exist for billions of years. They wait with the patience of deep time, suspended in an atmosphere that holds them like a planetary embrace, slowly cooling degree by degree toward the moment when they will finally fall. Scientists still debate exactly how long this superheated phase lasted. Some models suggest the surface remained molten for millions of years. Others propose hundreds of millions. The uncertainty reflects how little physical evidence survives from this epoch. Any rocks that formed during the Hadean were long ago recycled through plate tectonics or melted in subsequent bombardments. Only took geology 4 billion years to erase most of its own earliest chapters. The water waits, the planet cools, and in the vast silence of deep time, the stage prepares for Earth's first rain. The planet breathes in slow motion. Somewhere in the depths of this steaming atmosphere, a process as gentle as planetary sighing begins to unfold. Water vapor rises from the molten surface, carrying with it the heat that has kept Earth's early sky in perpetual summer for millions of years. But now, grain by grain, degree by degree, something shifts. The first stirrings of what scientists call atmospheric stratification begin to separate the dense steam into layers, each with its own temperature, its own density, its own patient chemistry, at altitudes where the air pressure equals what future mountain tops will know. The water vapor encounters conditions unlike anything in the lower atmosphere. Here, 60 kilometers above the glowing surface, temperatures drop to merely 600 degrees Celsius. For water molecules accustomed to the crushing heat below, this represents a kind of liberation. They move more slowly, cluster more readily, begin to exhibit behaviors that hint at the liquid state that remains centuries away. The physics governing these high-altitude water molecules follows rules that seem almost contradictory. Despite temperatures that would vaporize lead, the extreme atmospheric pressure keeps the water in a state that exists nowhere else in the solar system, neither quite gas nor quite liquid. But something in between that modern science calls a supercritical fluid. These water molecules flow like liquid but expand like gas, creating currents and eddies that swirl through the upper atmosphere with the consistency of thin syrup. Convection drives this atmospheric circulation with relentless efficiency. Heat from the molten surface creates updrafts that carry water vapor into the cooler regions above, where it releases its energy and begins to sink back toward the surface. This creates enormous circulation cells that span thousands of kilometers, moving water through vertical distances that dwarf any mountain range Earth will ever build. The rising vapor carries heat upward at the rate of several degrees per kilometer, while the descending flow brings cooler, denser steam back toward the molten ground. Only took atmospheric physics a few million years to sort itself into these patterns. The irony of such organization emerging from apparent chaos speaks to the deep mathematical structures that govern planetary atmospheres, even in conditions that push beyond the limits of terrestrial experience. Fluid dynamics finds ways to create order, to establish circulation patterns that will persist for geological ages. These early atmospheric currents carve invisible channels through the steam, pathways that guide water vapor through cycles of rising and sinking that mirror the ocean currents that will one day flow beneath them. Scientists puzzle over the precise chemistry occurring in these high-altitude regions. The water vapor interacts with trace amounts of hydrogen, methane, ammonia, and other compounds released from the planet's interior. Some of these reactions produce complex organic molecules, the building blocks of future biochemistry, forming in the sterile heat of a world not yet ready for life. Other reactions consume these same compounds, breaking them down into simpler elements that drift back toward the surface to begin the cycle again. The mystery deepens when considering the role of cosmic radiation in these high-altitude chemical reactions. Without a magnetic field to deflect charged particles from space, early Earth's upper atmosphere experiences constant bombardment by cosmic rays. These high-energy particles strike water molecules with enough force to break hydrogen-oxygen bonds, creating free radicals that react violently with surrounding compounds. The result is a chemistry laboratory operating under conditions that no earthly experiment can replicate, producing compounds that may have no modern analog. Temperature measurements from this epoch would show gradients that challenge intuition. Near the molten surface, the air temperature exceeds the melting point of gold. At the very top of the atmosphere, where steam finally gives way to the vacuum of space, temperatures drop to nearly absolute zero. Between these extremes, the water vapor experiences every possible thermal condition, creating microenvironments where different phases of matter coexist in delicate equilibrium. The atmospheric pressure at these intermediate altitudes creates conditions that seem to violate everyday experience with water. At 50 kilometers above the surface, water molecules exist at pressures high enough to compress them into densities approaching that of liquid water, while temperatures remain hot enough to keep them in constant motion. This supercritical water exhibits properties that blur the boundaries between phases. It flows like liquid but compresses like gas, conducts heat like metal but remains transparent like vapor. Convection patterns in this supercritical layer create the first weather systems in Earth's history, though they bear no resemblance to familiar meteorology. Massive storms of superheated water vapor spiral through the upper atmosphere, driven by temperature differentials and the planet's rapid rotation. These proto-hurricanes carry no rain, produce no clouds visible from space, but they redistribute heat and water vapor across the planet with the efficiency of a global circulatory system. The planet's rapid rotation, still completing each day in 6 hours, creates Coriolis effects that twist these atmospheric currents into complex spiral patterns. Water vapor rising from the equatorial regions curves toward the poles, carrying heat from the hottest parts of the molten surface to regions where slightly cooler temperatures allow the first hints of atmospheric condensation. This poleward transport of heat prevents the formation of extreme temperature gradients that might destabilize the atmospheric circulation entirely. Modern climate models struggle to simulate these conditions accurately. The extreme temperatures, pressures, and chemical compositions push beyond the ranges where standard atmospheric equations remain valid. Scientists must extrapolate from laboratory experiments and theoretical calculations, creating computer simulations that approximate the behavior of water vapor under conditions that existed nowhere else in the solar system. Only took planetary science a century to realize how much it still doesn't understand about its own planet's earliest atmosphere, yet patterns emerge from this complexity. The rising and sinking of water vapor creates the first semblance of atmospheric layers, distinct regions with their own characteristic temperatures and pressures. These protostratospheres will persist for millions of years, slowly evolving as the planet continues to cool. The water vapor trapped within them carries the memory of its molten origins while anticipating its liquid future, suspended in a state of atmospheric patience that spans geological time. Above it all, the steam rises and falls in cycles that dwarf human comprehension. Each water molecule completes this vertical journey thousands of times, riding the thermal currents upward into the cooler realms, then sinking back toward the heat of the surface, carrying with it the energy that drives the planet's atmospheric engine. The water waits, circulating through conditions that grow imperceptibly cooler with each passing millennium, approaching the moment when circulation will give way to precipitation, when rising steam will finally condense into falling rain. In the vast theater of the upper atmosphere, something unprecedented begins to unfold. 65 kilometers above the molten surface, where the crushing density of steam finally starts to thin into something approaching the familiar vacuum of space. Individual water molecules encounter conditions that will change the course of planetary history. Here, for the first time since Earth's formation, temperatures drop below the critical threshold where water vapor can begin the slow transformation that leads to liquid droplets. The process starts with the quantum mechanics of molecular attraction. Water molecules, each composed of one oxygen atom flanked by 2 hydrogen atoms, possess a subtle electrical asymmetry that becomes crucial at these cooler temperatures. The oxygen end carries a slight negative charge, while the hydrogen ends lean slightly positive. In the extreme heat of the lower atmosphere, thermal energy overwhelms these weak electrical attractions. But here, in the marginally cooler realm of the high atmosphere, molecules begin to sense each other's presence across the tiny distances that separate them. 2 water molecules, tumbling through the thin steam, approach each other at precisely the right angle and velocity. Their electrical fields align, hydrogen from one molecule reaching toward oxygen on another, creating what chemists call a hydrogen bond. This connection lasts perhaps a nanosecond before thermal motion tears them apart again. But in that brief instant, something new exists in Earth's atmosphere, the first molecular cluster, the ancestor of every raindrop that will ever fall. These momentary aggregations occur billions of times each second throughout the upper atmosphere, water molecules finding each other and losing each other in an endless dance of formation and dissolution. Most clusters contain only 2 or 3 molecules before thermal energy disrupts them. Occasionally, under precisely the right conditions of temperature and pressure, a cluster survives long enough to attract a 4th molecule, then a 5th. These larger aggregations exist for microseconds at most, but their formation represents a fundamental shift in atmospheric physics water vapor, beginning its first tentative steps toward condensation. The chemistry governing cluster formation operates at the boundary between order and chaos. Temperature fluctuations of even a few degrees determine whether molecular clusters can form at all. At 580 degrees Celsius, the thermal energy proves too intense for hydrogen bonds to persist. At 570 degrees, clusters form and dissolve in rapid succession. At 560 degrees, a temperature that exists only in narrow bands within the upper atmosphere, clusters occasionally grow large enough to contain dozens of water molecules before thermal motion tears them apart again. Scientists still debate the precise mechanisms that allow these early clusters to form in such hostile conditions. Laboratory experiments can recreate the temperature and pressure, but not the complex interactions with volcanic gases and cosmic radiation that characterize Earth's early atmosphere. Computer simulations suggest that trace amounts of sulfur compounds might act as condensation nuclei, providing surfaces around which water molecules can more easily aggregate. Other models propose that cosmic ray impacts create ionized regions where electrical forces temporarily overcome thermal motion. Only took atmospheric chemistry 4 billion years to reveal these secrets to human understanding. The irony lies in studying Earth's most ancient processes, using the planet's most modern technology, supercomputers, modeling molecular interactions that occurred when the solar system itself was barely past infancy. Each simulation requires millions of calculations to track the behavior of individual water molecules through a few nanoseconds of cluster formation. Yet these brief interactions shape the atmospheric evolution that led to oceans. The vertical structure of the early atmosphere creates distinct zones where cluster formation becomes possible. Between 60 and 70 kilometers altitude, a narrow band exists where temperatures hover at the crucial threshold for molecular aggregation. Below this zone, thermal energy remains too intense. Above it, the atmospheric density drops so low that water molecules rarely encounter each other at all. Within this thin shell of possibility, the first tentative steps toward condensation play out against a backdrop of planetary cooling. Atmospheric circulation carries these early molecular clusters through complex three-dimensional pathways. Rising thermal currents transport them upward into regions where decreasing pressure and temperature allow them to grow larger before thermal motion disrupts them. Descending flows carry the fragments back toward the denser, hotter regions where they dissolve back into individual water molecules. This vertical mixing creates a kind of atmospheric laboratory where the same water molecules experience repeated cycles of clustering and dissociation. The temporal scales involved stretch beyond intuitive comprehension. An individual water molecule might participate in thousands of clustering events during a single journey through the upper atmosphere. Each cluster formation lasts microseconds, separated by minutes or hours of random thermal motion. Over geological time, these brief moments of molecular organization accumulate into something approaching statistical inevitability given enough attempts. Some clusters will eventually grow large enough to survive the thermal disruption that destroys their smaller cousins. Modern understanding of nucleation theory suggests that cluster formation follows probability distributions that depend critically on local atmospheric conditions. Small variations in temperature, pressure, or chemical composition dramatically affect the likelihood that molecular clusters will form and persist. In Earth's early atmosphere, these conditions fluctuate constantly due to volcanic outgassing, solar radiation, and the complex convection patterns that mix steam throughout the vertical column. The mystery deepens when considering the role of atmospheric turbulence in cluster formation. The rapid rotation of early Earth creates powerful wind shears that generate microscopic vortices throughout the upper atmosphere. These tiny whirlpools of moving gas can trap water molecules in regions of locally reduced thermal motion, creating brief pockets where cluster formation becomes more likely. The physics governing these microenvironments remains poorly understood, requiring mathematical tools that can describe fluid motion at molecular scales. Each successful cluster formation represents a victory of organization over entropy, molecular cooperation overcoming thermal chaos. The hydrogen bonds that hold these clusters together store energy borrowed from the planet's cooling process. Each degree of atmospheric cooling increases the probability that molecular clusters will form and persist. In this sense, the early clustering of water molecules serves as a kind of atmospheric memory, preserving information about the planet's thermal history in the fleeting architecture of molecular aggregation. The clusters themselves remain invisible to any hypothetical observer. Even the largest aggregations contain fewer molecules than would be needed to scatter visible light. They exist as purely chemical phenomena, temporary arrangements of matter that alter the statistical behavior of atmospheric water vapor without producing any visible signs of their presence. Only their cumulative effect on atmospheric heat transport hints at their existence. Subtle changes in convection patterns that suggest something new occurring in the cooling sky. As thermal energy continues its slow escape to space, these molecular clustering events become more frequent, more persistent, more complex. The same water molecules that have circulated through the superheated atmosphere for millions of years begin to exhibit new behaviors. New tendencies toward aggregation that point toward a future when clustering will give way to condensation, when invisible molecular aggregations will grow into visible droplets, when the patient water vapor will finally begin its transformation into rain. Above the molecular clusters that wink in and out of existence in Earth's upper atmosphere, a transformation of grander scale begins to unfold. The same atmospheric cooling that allows water molecules to find each other in brief, hydrogen-bonded embraces now enables something unprecedented in planetary history: the formation of the first clouds. These are not clouds as any future observer would recognize them, not the billowing white formations that will one day cast shadows on green landscapes, but massive accumulations of water vapor so dense they begin to bend light, so extensive they span continents, so persistent they endure for centuries without dissipating. The physics of cloud formation in Earth's early atmosphere operates under conditions that challenge conventional meteorology. At altitudes where atmospheric pressure equals 50 times that of future sea level, water vapor concentrates into densities that approach the liquid state while maintaining temperatures hot enough to melt tin. These protoclouds exist in a phase of matter that has no modern analog, neither gas nor liquid, but something between, suspended in atmospheric conditions that will never occur again in Earth's history. The formation process begins when rising thermal currents carry water vapor into regions where molecular clustering becomes statistically inevitable. Unlike the brief, microscopic aggregations that form and dissolve in nanoseconds, these high-altitude concentrations of water vapor achieve densities that allow clusters to merge with other clusters, creating larger assemblages that persist for minutes, then hours, then days. The transition from isolated molecular clusters to coherent cloud formations occurs gradually, imperceptibly, like the slow accumulation of atmospheric memory. Scientists theorize that trace amounts of sulfuric acid, produced by interactions between water vapor and volcanic sulfur compounds, serve as condensation nuclei around which the earliest cloud droplets form. These acid molecules, dispersed throughout the upper atmosphere by convection currents, provide surfaces that attract water molecules more readily than the empty space that surrounds them. Each acid nucleus becomes the seed around which hundreds, then thousands of water molecules aggregate into the first recognizable cloud particles. Only took atmospheric chemistry a few 100 million years to stumble upon this solution to the nucleation problem. The irony lies in sulfuric acid, a compound that will later prove hostile to most forms of life, serving as the catalyst that enables cloud formation, the atmospheric process that will eventually deliver the water necessary for life's emergence. These early clouds owe their existence to the same volcanic outgassing that maintains Earth's surface in molten chaos, a connection between destruction and creation that threads through planetary evolution. The vertical extent of these first clouds stretches across atmospheric layers that span dozens of kilometers. Unlike future clouds that form in narrow altitude bands, Earth's early cloud systems extend from the upper reaches of the steam-saturated atmosphere down to altitudes where increasing pressure compresses the water vapor back into supercritical states. Within this vast vertical column, different regions of the same cloud system experience dramatically different physical conditions, creating internal circulation patterns that have no comparison in modern meteorology. Atmospheric circulation drives these early clouds through migration patterns that circle the globe. The planet's rapid rotation, combined with massive convection cells that transport heat from the molten surface to the upper atmosphere, creates wind systems that carry cloud formations across thousands of kilometers before thermal processes dissipate them back into invisible water vapor. Some clouds persist for months, drifting slowly through the orange-brown sky like atmospheric continents, accumulating water vapor and releasing it in cycles that begin to regulate the planet's heat distribution. The optical properties of these early clouds remain one of atmospheric science's quiet mysteries. The extreme temperatures and pressures alter how water molecules interact with electromagnetic radiation, creating light-scattering behaviors that differ from those observed in modern clouds. Computer models suggest that these protoclouds might have appeared nearly transparent to visible light while strongly absorbing infrared radiation, making them invisible to hypothetical observers on the surface but crucial components in the planet's evolving energy balance. Temperature gradients within individual cloud systems create complex internal dynamics that drive their own weather patterns. Cooler regions near the cloud tops allow more persistent molecular clustering, while warmer zones nearer the surface maintain water in more vapor-like states. These temperature differences generate convection currents within the clouds themselves, creating circulation systems nested within the larger atmospheric flows that carry the clouds across the planet's surface. The chemical composition of these early clouds reflects the complex atmospheric chemistry of the Hadean epoch. In addition to water vapor and sulfuric acid nuclei, they contain trace amounts of hydrogen sulfide, carbon dioxide, methane, and dozens of other compounds released by volcanic outgassing. Some of these chemicals catalyze cluster formation, making cloud development more likely. Others inhibit aggregation, creating regions within the same cloud where water molecules remain more dispersed. The result is atmospheric heterogeneity on scales ranging from molecular to continental. Modern climate models struggle to simulate the behavior of these early cloud systems accurately. The extreme conditions push beyond the parameter ranges where standard atmospheric equations remain valid, requiring extrapolations that introduce significant uncertainties into any predictions about cloud lifetime, distribution, or internal structure. Laboratory experiments can recreate some aspects of early cloud chemistry, but not the complex three-dimensional dynamics that govern their formation and dissipation in planetary atmospheres. The persistence of these early clouds depends critically on the balance between condensation and evaporation processes, operating under conditions that exist nowhere else in the solar system. In the upper regions of cloud systems, Cooling allows continued water vapor aggregation, adding mass to the cloud structure. In the lower regions, heating from the molten surface below drives evaporation that removes water vapor and reduces cloud density. The altitude where these processes balance determines whether individual clouds grow larger or gradually dissipate back into the surrounding atmosphere. Gravitational effects begin to play a role in cloud dynamics as water vapor concentrations reach densities that approach those of liquid water. The accumulated mass of water vapor in large cloud systems creates subtle gravitational attractions that influence atmospheric circulation patterns on regional scales. These effects remain small compared to the thermal forces that dominate atmospheric motion, but they represent the first hints of how water's physical presence will eventually reshape planetary dynamics through mechanisms ranging from tidal forces to ice sheet formation. The temporal evolution of individual cloud systems follows patterns that reflect the underlying atmospheric cooling process. Early in their formation, clouds consist primarily of loosely aggregated molecular clusters held together by weak hydrogen bonds. As atmospheric temperatures continue to decrease, the clusters within clouds achieve greater stability, persisting for longer periods before thermal motion disrupts them. This gradual transition from ephemeral to persistent clustering within cloud systems mirrors the broader atmospheric evolution that leads toward conditions where liquid water can exist. Solar radiation interacts with these early cloud formations in ways that influence both their internal structure and their role in planetary energy balance. High-energy photons from the young sun can break apart the weak hydrogen bonds that hold molecular clusters together, leading to cloud dissipation during periods of intense solar activity. Lower-energy infrared radiation gets absorbed and re-radiated by the water vapor, creating heating effects that drive internal circulation within cloud systems and contribute to their eventual dispersal. As millions of years pass, these early cloud formations become more frequent, more persistent, more widespread. The same atmospheric cooling that enables their formation also increases their longevity, creating a positive feedback loop where cloud formation becomes increasingly likely as temperatures continue to drop. The sky begins to fill with these invisible formations, massive accumulations of water vapor that drift through the orange-brown atmosphere like ghosts of future storms, carrying within their ephemeral structure the potential for the first drops of rain that will eventually fall on cooling stone. Time moves differently in the Hadean atmosphere. Millions of years pass like seasons, each millennium bringing Earth's surface temperature down by fractions of a degree, each degree opening new possibilities for water vapor suspended in the cooling sky. The early clouds that formed in the upper atmosphere now persist for decades before dissipating, their lifespans measured not in the hours or days that will characterize future weather systems, but in geological timespans that dwarf human comprehension. Throughout these extended atmospheric ages, water vapor maintains its patient circulation between the molten surface and the gradually cooling heights above. The temperature gradient that drives atmospheric circulation has begun to stabilize into patterns that will persist for millions of years. Surface temperatures still exceed 1,000 degrees Celsius, hot enough to keep solid rock in a liquid state, while the uppermost reaches of the atmosphere approach temperatures where water vapor can begin to exhibit behaviors that hint at phase transitions. This thermal structure creates circulation cells of unprecedented scale, massive vertical flows that transport water vapor through temperature ranges equivalent to the difference between Arctic ice and tropical heat. Within these circulation patterns, individual water molecules experience thermal histories that span the full range of conditions possible in planetary atmospheres. A molecule that begins its journey in the superheated regions near the molten surface rises through zones of decreasing temperature and pressure, spending perhaps months in transit through the atmospheric column. During this ascent, The same molecule participates in countless clustering events, briefly joining with other water molecules in aggregations that form and dissolve as thermal conditions fluctuate around the critical thresholds for hydrogen bond formation. The mysteries of atmospheric residence time become apparent when considering the average duration that water molecules spend in different regions of the early atmosphere. Computer simulations suggest that water vapor near the surface circulates rapidly, driven by intense convection currents that mix the dense steam in cycles measured in weeks or months. In contrast, water vapor that reaches the upper atmosphere may remain at those altitudes for years or decades before convection carries it back toward the surface, creating atmospheric layers with distinct chemical compositions and thermal histories. Scientists puzzle over the precise mechanisms that govern these extended circulation patterns. The extreme atmospheric density, perhaps 60 times greater than modern Earth's atmosphere, creates circulation dynamics that have no contemporary analog. Thermal energy moves through this dense medium by mechanisms that combine convection, conduction, and radiation in proportions that shift with altitude and temperature. Only took atmospheric physics 4 billion years to develop instruments sensitive enough to detect the subtle signals that preserve information about these ancient processes in modern atmospheric chemistry. The chemical evolution occurring within these long-term circulation patterns adds complexity to the already intricate dance of molecular clustering and dissociation. Water molecules interact with trace compounds released by volcanic outgassing, creating chemical reactions that occur over timescales ranging from microseconds to centuries. Some reactions produce compounds that catalyze cluster formation, while others generate molecules that inhibit aggregation. The net effect varies with altitude, temperature, and the specific mixture of gases present at any given location and time. Atmospheric stratification becomes more pronounced as the planet continues its slow cooling process. Distinct layers develop at altitudes where specific temperatures create optimal conditions for different types of molecular behavior. Near the surface, thermal energy remains too intense for any persistent clustering. At intermediate altitudes, molecular clusters form and dissolve in rapid succession. In the uppermost regions, clusters achieve greater stability and begin to merge into larger aggregations that persist for increasingly longer periods before thermal motion disrupts them. The optical properties of the atmosphere begin to change as water vapor concentrations and cluster densities shift with altitude and time. Regions with higher concentrations of molecular clusters scatter light differently than areas dominated by individual water molecules, creating subtle variations in atmospheric transparency that alter how solar energy penetrates to different depths. These optical changes, while barely detectable, influence the thermal structure of the atmosphere and contribute to the complex feedback loops that govern atmospheric evolution. Pressure effects become increasingly important as atmospheric cooling allows water vapor to achieve higher densities without immediate transition to supercritical states. At altitudes where atmospheric pressure equals 30 times that of future sea level, water vapor exhibits behaviors that blur the boundary between gas and liquid phases. Molecules move more slowly, interact more frequently, and maintain closer proximity to their neighbors than in the lower pressure regions above. These high-density zones serve as transition regions where the physics of gas behavior gradually gives way to dynamics more characteristic of liquid systems. The role of atmospheric turbulence in mixing water vapor between different temperature and pressure zones becomes crucial for understanding how the early atmosphere maintains chemical and thermal equilibrium. Convection currents create turbulent eddies that span scales from molecular to continental, stirring water vapor through complex three-dimensional patterns that ensure thorough mixing between atmospheric layers. This turbulent transport prevents the formation of stable stratification that might inhibit the vertical circulation necessary for continued atmospheric cooling. Modern climate models attempting to simulate these conditions must account for feedback mechanisms that operate on timescales ranging from seconds to millions of years. Molecular clustering affects atmospheric heat transport, which influences convection patterns, which determine cluster formation rates, creating feedback loops that can either stabilize or destabilize atmospheric circulation. The mathematical complexity of these coupled processes requires computational resources that push the limits of current supercomputing capabilities, yet the results remain uncertain due to the lack of empirical data from this ancient epoch. The persistence of water vapor in the early atmosphere represents a kind of atmospheric memory that preserves information about the planet's thermal evolution. Each water molecule carries within its thermal motion a record of the temperatures it has experienced during its atmospheric residence. Statistical analysis of molecular velocities at different altitudes reveals information about heat transport mechanisms and circulation timescales that operated millions of years ago. Only took statistical mechanics a century to develop the theoretical framework necessary to extract this information from molecular behavior. Energy balance calculations suggest that atmospheric cooling during this epoch occurs at rates determined by the efficiency of heat transport from the molten surface to the upper atmosphere, where radiation to space can remove thermal energy from the planetary system. Water vapor serves as the primary medium for this heat transport, carrying thermal energy upward through convection and releasing it at altitudes where radiative cooling becomes effective. The cooling rate depends critically on atmospheric circulation efficiency, which in turn depends on the complex dynamics of water vapor behavior under extreme conditions. Regional variations in atmospheric cooling create geographic patterns in water vapor behavior that persist for geological timescales. Areas above particularly active volcanic regions maintain higher surface temperatures, creating enhanced convection that transports water vapor more rapidly to cooling altitudes. Regions above areas of reduced volcanic activity experience slower circulation, allowing water vapor to spend more time at intermediate altitudes where clustering becomes more likely. These geographic variations in atmospheric dynamics create spatial patterns in water vapor distribution that influence the eventual locations where condensation will first become possible. The gradual shift from ephemeral to persistent molecular clustering throughout the atmospheric column signals the approach of a fundamental transition in planetary evolution. The same atmospheric cooling that enables longer-lived clusters also increases the probability that clusters will grow large enough to exhibit collective behaviors characteristic of droplet formation. As temperatures continue their imperceptible decline, the statistical inevitability of this transition approaches somewhere in the vast atmospheric laboratory above the molten Earth. Conditions are approaching the threshold where clustering will give way to condensation, where invisible molecular aggregations will grow into visible droplets, where patient water vapor will finally begin its transformation into falling rain. The transition arrives without ceremony, unmarked by any atmospheric fanfare that might announce its significance to the cooling planet below. Somewhere between the 600th and 700th million year of Earth's existence, surface temperatures drop below a critical threshold that has been approaching with geological patience. For the first time since the planet's formation, regions of the cooling crust achieve temperatures low enough that water droplets, should they somehow form and fall from the sky above, might survive contact with solid rock for more than a few milliseconds before flashing back into steam. This thermal milestone passes unnoticed through an atmosphere that continues its ancient circulation patterns, carrying water vapor through the same vertical journeys that have characterized atmospheric dynamics for hundreds of millions of years. Yet something fundamental has shifted in the relationship between the cooling surface and the water-laden sky above. The relentless heat that has kept liquid water an impossibility throughout Earth's early history has finally retreated enough to create zones where the phase transition from vapor to liquid might persist, however briefly, against the thermal energy radiating from cooling basalt. The surface itself presents a landscape that defies familiar description. The continuous ocean of molten rock that characterized earlier epochs has given way to a complex mosaic of cooling lava flows, solidified basalt plains, and regions where magma still reaches the surface through volcanic vents and fissures. Surface temperatures vary dramatically across this volcanic terrain. Some areas maintain temperatures above 800 degrees Celsius, while others, particularly those recently emerged from the subsurface heat, cool toward the critical 500-degree threshold where liquid water becomes theoretically possible. Scientists estimate that perhaps 5% of Earth's surface during this epoch consists of solid rock cool enough to allow momentary water contact without immediate vaporization. These cooled regions form irregular patches scattered across the predominantly molten landscape, creating a planetary surface that resembles a vast cooling forge where pockets of black basalt emerge from glowing orange flows like islands of possibility in an ocean of heat. The thermal contrast between these regions creates complex convection patterns in the overlying atmosphere that will influence where the first raindrops eventually fall. The atmospheric response to surface cooling manifests in subtle changes to circulation patterns that have remained stable for geological ages. Regions above cooler surface areas experience reduced thermal input, creating zones of relative atmospheric stability where water vapor can accumulate without the intense convection that characterizes areas above molten rock. These atmospheric cool spots become preferential locations for the formation of persistent molecular clusters and the early cloud formations that herald the approach of condensation. Only took planetary thermodynamics several 100 million years to reach this delicate balance between surface cooling and atmospheric saturation. The irony lies in the precision required. Surface temperatures must cool enough to allow liquid water survival, while atmospheric water vapor concentrations must remain high enough to support droplet formation. Too much cooling, and the atmospheric circulation that maintains water vapor aloft begins to collapse. Too little cooling, and any water droplets that form will immediately vaporize upon surface contact. The physics governing heat transfer between the cooling surface and the water-saturated atmosphere involves mechanisms that operate across vastly different spatial and temporal scales. Molecular-level interactions between water molecules and hot basalt occur in nanoseconds, while the geological processes that control surface cooling operate over millions of years. The intersection of these different timescales creates opportunities for metastable states where liquid water might briefly exist in thermal environments that would seem to prohibit its formation. Temperature gradients in the shallow atmospheric layers above cooling basalt create microenvironments where water vapor experiences rapid thermal transitions as it approaches the surface. A water molecule descending through the last few meters of atmosphere might encounter temperature changes of hundreds of degrees within seconds, passing through thermal conditions that favor clustering, then droplet formation, then immediate revaporization as it approaches the hot rock below. These thermal shocks produce complex chemical reactions that release energy and contribute to the atmospheric turbulence above cooling volcanic landscapes. The chemical composition of the early atmosphere plays a crucial role in determining how water droplets will behave when they eventually encounter cooling rock surfaces. Dissolved volcanic gases, particularly sulfur compounds and carbon dioxide, alter the thermal properties of water vapor and affect the temperature thresholds where phase transitions become possible. Atmospheric chemistry models suggest that these dissolved gases might actually facilitate droplet survival by creating buffer zones where thermal energy gets absorbed by chemical reactions rather than transmitted directly to water molecules. Modern understanding of nucleate boiling theory provides insights into the complex physics that governs water droplet behavior on superheated surfaces. When liquid water contacts rock at temperatures above its boiling point, the rate of heat transfer determines whether the droplet will survive long enough to spread across the surface or will immediately explode back into vapor. The texture and chemical composition of cooling basalt surfaces create microscopic variations in heat transfer efficiency that could allow some droplets to persist for seconds rather than milliseconds. Surface tension effects become critically important when considering how the first water droplets might behave upon contact with cooling rock. The extreme temperature differentials create rapid changes in surface tension that cause droplets to exhibit dynamic behaviors unlike anything observed under normal terrestrial conditions. Computer simulations suggest that droplets might oscillate between spherical and flattened configurations as thermal energy creates internal convection currents that redistribute heat throughout the droplet volume. The mystery deepens when considering the role of atmospheric pressure in droplet formation and survival near the cooling surface. The dense early atmosphere creates pressure conditions that raise the boiling point of water significantly above its value under standard conditions. At atmospheric pressures 50 times greater than modern Earth, water remains liquid at temperatures that would cause immediate vaporization under normal circumstances. This pressure effect creates a narrow window of opportunity where liquid droplets might survive contact with surfaces that would otherwise prove too hot for water persistence. Volcanic outgassing continues to complicate the thermal landscape by creating localized atmospheric disturbances that affect both temperature and pressure in unpredictable ways. Volcanic vents release superheated gases that create thermal plumes extending high into the atmosphere, while other areas experience relative atmospheric calm where cooling proceeds more uniformly. These variations in volcanic activity create a constantly shifting mosaic of thermal conditions that influence where droplet survival becomes most likely. The statistical nature of molecular clustering in the cooling atmosphere means that droplet formation events occur randomly across both space and time. Some regions of the atmosphere might experience bursts of cluster formation that produce numerous small droplets, while other areas remain dominated by individual water molecules for extended periods. This randomness, combined with the irregular distribution of surface cooling, creates a planetary system where the first successful water droplet contact with solid rock becomes a matter of statistical inevitability rather than predictable occurrence. Atmospheric circulation patterns transport water vapor from regions above hot volcanic areas to zones above cooling rock surfaces, creating opportunities for droplets formed in cooler atmospheric regions to encounter surface areas where survival becomes possible. The three-dimensional nature of these transport processes means that droplets formed at high altitudes above hot surfaces might eventually descend through atmospheric currents that carry them over cooling rock areas where thermal conditions favor their persistence. As surface cooling continues its imperceptible progress, the fraction of Earth's surface that can potentially support momentary liquid water contact gradually increases. Each degree of cooling expands the geographic extent of surface areas where droplet survival becomes theoretically possible, while simultaneously creating atmospheric conditions that favor more frequent and persistent droplet formation. The convergence of these trends points toward an inevitable moment when atmospheric water vapor and surface thermal conditions will align to produce Earth's first successful contact between liquid water and solid rock, the prelude to the planet's first rainfall. The moment arrives with the silence of deep time, unmarked by any witness save the cooling planet itself. somewhere above a patch of freshly solidified basalt that has spent the last 1,000 years cooling from orange heat to black stone. A water droplet forms in the dense atmosphere and begins its historic descent. This droplet, barely a millimeter across and containing perhaps 1 billion water molecules, represents the culmination of processes that have been building for hundreds of millions of years: the convergence of atmospheric cooling, surface solidification, and molecular physics that makes liquid water possible on Earth for the first time since the planet's formation. The droplet's formation follows pathways that have become increasingly probable as atmospheric temperatures continue their gradual decline. In the upper reaches of the atmosphere, where molecular clustering has grown more persistent with each passing millennium, water vapor accumulates around a microscopic grain of sulfuric acid that serves as a condensation nucleus, molecule by molecule. The cluster grows beyond the critical size where surface tension forces overcome thermal motion, creating a stable droplet that can survive the thermal fluctuations of its atmospheric environment. As the droplet begins its fall through the dense early atmosphere, it encounters conditions unlike anything that will exist in Earth's later meteorological history. The atmospheric pressure, still nearly 60 times greater than future sea level conditions, compresses the droplet into a density approaching that of liquid mercury while maintaining the transparency and fluidity of water. Surface tension forces, enhanced by the extreme pressure, create a droplet that behaves more like a tiny sphere of liquid metal than the soft, easily deformed water droplets of familiar experience. The physics of droplet motion through the dense atmosphere follows rules that challenge conventional understanding of terminal velocity and fluid dynamics. Atmospheric drag forces, proportional to the square of the fluid density, create resistance that slows the droplet's descent to speeds measured in centimeters per second rather than the meters per second characteristic of modern rainfall. This slow descent takes hours rather than minutes, giving the droplet extended exposure to atmospheric conditions that gradually modify its temperature and chemical composition during the journey toward the surface. Chemical reactions occur within the falling droplet as it encounters trace compounds dispersed throughout the early atmosphere. Dissolved sulfur dioxide creates dilute sulfuric acid that alters the droplet's freezing and boiling points, while carbon dioxide forms weak carbonic acid that affects surface tension and evaporation rates. These chemical modifications, occurring continuously during the droplet's atmospheric journey, prepare it for the thermal shock that awaits when it finally contacts the cooling rock surface below. Scientists puzzle over the precise sequence of events that occurs when this first droplet strikes the basalt surface. Computer models suggest that the initial contact creates a microscopic explosion of steam as the droplet's surface layer vaporizes instantly upon touching rock that still radiates heat at temperatures above 300 degrees Celsius. Yet, the extreme atmospheric pressure and the droplet's chemical modifications might allow its core to survive this initial thermal shock, creating a brief moment where liquid water and solid rock coexist on Earth's surface for the first time in planetary history. Only took planetary evolution several 100 million years to orchestrate this meeting between water and stone. The irony lies in the brevity of the encounter. A droplet that required eons of atmospheric development to form survives perhaps a second in contact with cooling rock before thermal energy converts it back to steam. Yet, in that brief moment, fundamental changes occur in both the water and the rock that will influence chemical processes for millions of years to come. The thermal dynamics of droplet impact operate on timescales that span orders of magnitude. The initial contact between water and hot rock occurs in microseconds, creating shock waves that propagate through both materials at the speed of sound. Heat transfer from rock to water operates on millisecond timescales, creating temperature gradients that drive explosive boiling. The complete vaporization of the droplet requires perhaps a full second, an eternity in the context of molecular collision processes, but an instant in the context of geological change. Surface chemistry begins to play a role as the vaporizing droplet leaves behind trace amounts of dissolved minerals that alter the thermal properties of the basalt surface. These microscopic deposits create nucleation sites that affect how future droplets will behave when they encounter the same surface areas. Over thousands of droplet impacts, these chemical modifications accumulate into surface treatments that gradually improve the thermal tolerance of water-rock interactions. The acoustic signature of droplet impact creates sound waves that propagate through the dense atmosphere with frequencies and amplitudes unlike anything in Earth's future acoustic environment. The combination of extreme atmospheric density and the specific thermal dynamics of water vaporization produces sounds that range from ultrasonic frequencies generated by explosive boiling to low-frequency rumbles created by atmospheric turbulence around the impact site. These sounds travel for kilometers through the dense air, creating the first atmospheric noises in Earth's history that result from water surface interactions. Atmospheric disturbances generated by droplet impact create localized weather patterns that influence subsequent droplet formation and trajectory. The thermal energy released when liquid water converts to steam creates updrafts that carry water vapor back into the cooling atmosphere, where it can participate in new cycles of clustering and droplet formation. These feedback loops between surface impact and atmospheric circulation establish the earliest forms of weather systems that connect surface conditions with atmospheric processes. The statistical nature of droplet formation means that the first successful water-rock contact is followed by similar events scattered randomly across the cooling surface. Each impact occurs independently, separated by hours or days, as atmospheric circulation patterns transport water vapor over different regions of cooling basalt. The cumulative effect of these isolated events begins to establish geographic patterns in surface chemistry and thermal modification that will influence the eventual development of more sustained precipitation. Modern experimental simulations of water droplet impact on superheated surfaces provide insights into the complex physics that governs these first water-rock interactions. High-speed photography reveals that droplets can exhibit bouncing behaviors on hot surfaces, making multiple contacts before finally vaporizing completely. Applied to early Earth conditions, these experiments suggest that some droplets might survive several impact cycles, spreading thin films of water across cooling rock surfaces before thermal energy finally overcomes surface tension and converts them back to vapor. The chemical composition of early atmospheric water vapor affects droplet behavior in ways that have no modern analog. Dissolved volcanic gases create water droplets with altered thermal properties that might allow them to survive longer on hot surfaces than pure water could. Trace amounts of metallic compounds, particularly iron and magnesium dissolved from atmospheric dust, create droplets that conduct heat more efficiently and might spread more readily across rock surfaces before vaporization. Regional variations in surface cooling create preferred locations where droplet survival becomes more likely. Areas above ancient impact craters, where surface disruption has enhanced heat dissipation, cool more rapidly than surrounding volcanic plains. Regions near the emerging edges of tectonic plates, where fresh rock surfaces are exposed to atmospheric cooling, offer thermal conditions that favor extended water-rock contact. These geographic variations in thermal hospitality begin to establish the first spatial patterns in Earth's hydrological processes. As millions of these isolated droplet impacts accumulate across the cooling surface, they begin to produce measurable changes in surface chemistry and thermal properties. Rock surfaces that experience repeated water contact develop microscopic texture modifications that improve heat dissipation and create more favorable conditions for future droplet survival. The gradual accumulation of these surface modifications prepares the planetary surface for the sustained water contact that will eventually characterize true rainfall. Each droplet impact represents a small victory of organization over thermal chaos. Liquid persistence against heat dissipation. The water molecules that briefly achieve liquid contact with solid rock carry within their ephemeral existence the memory of atmospheric circulation patterns that span continents and the anticipation of oceanic processes that remain millions of years in the future. These first tentative meetings between water and stone establish the chemical and physical foundations for hydrological processes that will eventually reshape the planet's surface through mechanisms ranging from chemical weathering to erosion, processes that begin with single droplets hissing into steam on cooling volcanic rock. In the aftermath of countless singular droplet impacts scattered across the cooling volcanic landscape, something subtle but profound begins to emerge. The random distribution of water-rock contacts gradually creates surface conditions that favor the accumulation of liquid water in the lowest lying areas of the irregular basalt terrain. Wherever ancient lava flows have created depressions, wherever tectonic forces have formed shallow valleys, wherever the natural topography of cooling rock creates pockets sheltered from the most intense surface heat, water droplets begin to survive long enough to flow together before vaporizing back into the dense atmosphere above. The physics governing this transition from isolated droplet impacts to persistent water accumulation involves complex interactions between surface tension, thermal conductivity, and the three-dimensional geometry of volcanic topography. Individual droplets that might survive only seconds on exposed basalt surfaces can persist for minutes when they collect in shallow depressions where the effective surface area for heat transfer decreases while the thermal mass of accumulated water increases. These thermal refugia become the sites where Earth experiences its first temporary pools of liquid water. The formation of these early pools follows patterns dictated by the irregular topography left by millions of years of volcanic activity. Lava flows create natural basins when molten rock flows around obstacles or when cooling rates vary across the surface, creating depressions that range from centimeters to meters in diameter. Impact craters from the late heavy bombardment provide ready-made basins with steep sides that concentrate falling droplets into small areas while minimizing exposure to radiant heat from surrounding rock surfaces. Temperature gradients within these shallow depressions create microenvironments where different regions of the same pool experience dramatically different thermal conditions. Water in the center of a depression, insulated by surrounding liquid and shielded from direct contact with the hottest rock surfaces, might achieve temperatures cool enough to remain liquid for extended periods. Water near the edges, in direct contact with hot basalt, boils continuously, creating circulation patterns that transport heat from the pool's margins toward its center. Scientists estimate that these first temporary pools might persist for hours or even days before thermal energy and evaporation reduce them back to water vapor. The longevity of individual pools depends critically on their depth, their surface area, and the thermal properties of the surrounding rock. Deeper pools benefit from greater thermal mass that resists rapid heating, while pools with smaller surface areas lose less water to evaporation. The optimal geometry for pool persistence, deep, narrow depressions with minimal surface exposure, becomes preferentially preserved as thermal selection favors certain topographic configurations over others. Only took hydrology several hundred million years to discover these optimal configurations through the trial and error of thermal selection. The irony lies in Earth's first water bodies being shaped not by familiar erosional processes, but by the thermal dynamics of liquid survival on a cooling planet. These early pools represent hydrological features that have no modern analogues, bodies of liquid water whose existence depends entirely on finding the right balance between thermal input and thermal dissipation in an environment still too hot for stable water persistence. The chemical evolution of water within these temporary pools occurs at accelerated rates due to the extreme temperatures and the concentrated interaction with volcanic rock surfaces. Dissolved minerals accumulate rapidly as hot water extracts compounds from basalt, creating chemical solutions that differ dramatically from future freshwater or seawater compositions. High concentrations of iron, magnesium, and sulfur compounds alter the thermal properties of the water itself, sometimes improving its ability to survive in high-temperature environments. Atmospheric interactions with pool surfaces create the first examples of evaporation-driven concentration processes that will later characterize saline lakes and salt flats. As water evaporates from pool surfaces, dissolved minerals become increasingly concentrated, raising the boiling point and improving thermal stability. Some pools develop surface crusts of precipitated minerals that provide thermal insulation and reduce evaporation rates, creating feedback mechanisms that enhance their own survival probability. The temporal dynamics of pool formation and dissipation follow patterns that reflect both atmospheric circulation and surface cooling rates. Periods of enhanced atmospheric clustering, driven by large-scale circulation patterns or volcanic activity, create episodes of increased droplet formation that can fill multiple pools simultaneously. Conversely, periods of reduced atmospheric water, vapor concentration, or increased surface heating can cause widespread pool evaporation, leaving behind only mineral deposits and modified rock surfaces that preserve evidence of temporary water presence. Modern understanding of nucleate boiling in confined geometries provides insights into the complex thermal processes that occur within these early pools. The interaction between liquid water and hot rock surfaces creates bubble nucleation that drives vigorous circulation within the pools, mixing water through convection patterns that enhance heat distribution and chemical dissolution. These circulation processes, while brief in duration, establish the first examples of fluid dynamics in terrestrial water bodies. The acoustic environment around these temporary pools creates soundscapes unlike anything in Earth's future hydrological systems. The continuous boiling at pool margins produces constant hissing and bubbling sounds that propagate through the dense atmosphere, while the thermal expansion and contraction of water creates pressure waves that generate low-frequency rumbles. These sounds represent Earth's first examples of water-generated acoustic phenomena, the earliest whispers of future rivers and waterfalls. Geographic clustering of pools occurs in regions where topographic conditions and thermal environments create optimal combinations of droplet collection and thermal survival. Ancient impact basins, particularly those with complex rim structures that create multiple nested depressions, become sites where numerous pools can form simultaneously. Areas where tectonic activity has created extensive fracture systems provide linear arrangements of depressions that channel water flow between connected pools before thermal energy overwhelms the system. The chemical fingerprints left by evaporated pools begin to create surface heterogeneity that influences future droplet behavior and pool formation. Mineral deposits alter the thermal conductivity of rock surfaces, creating regions where subsequent pools might persist longer or shorter periods depending on the specific chemical compositions involved. These surface modifications accumulate over millions of pool formation and evaporation cycles, gradually creating chemical landscapes that encode the history of early hydrological processes. Interaction between adjacent pools creates the first examples of surface water flow on Earth, when thermal conditions allow temporary connections between separate water bodies. Water spilling from one pool to another, driven by topographic gradients and thermal expansion, creates brief episodes of surface flow that represent the earliest streams on the planetary surface. These connections rarely persist for more than minutes before thermal energy vaporizes the connecting water, but they establish precedents for the surface water networks that will eventually drain entire continents. The biological implications of these temporary pools remain speculative but intriguing to astrobiologists studying early Earth conditions. While temperatures remain far too high for any known forms of life, the chemical concentration processes occurring within evaporating pools create conditions that might favor the formation of complex organic molecules. The rapid cycling between liquid and vapor phases might provide energy sources for chemical reactions that would be impossible under more stable thermal conditions. Statistical analysis of pool formation and survival reveals patterns that reflect the underlying probability distributions governing atmospheric droplet formation and surface thermal conditions. The frequency of pool formation follows the same statistical patterns as atmospheric clustering events, while pool longevity correlates with specific combinations of topographic and thermal variables. These statistical relationships begin to establish the mathematical frameworks that will eventually describe more complex hydrological processes. As surface cooling continues its imperceptible progression, the average lifetime of temporary pools gradually increases while their frequency of formation becomes more predictable. The same atmospheric and surface processes that enable pool formation become more reliable as thermal conditions approach ranges where liquid water persistence becomes statistically inevitable rather than thermally improbable. Each pool that forms and evaporates contributes to the gradual modification of surface conditions that prepares the planetary surface for more sustained water accumulation, for pools that will persist for seasons rather than days, for the eventual emergence of permanent water bodies that will endure for geological ages. The sky darkens with a promise that has been building for geological ages. Above the scattered temporary pools that mark Earth's surface like scattered mirrors reflecting orange twilight, atmospheric conditions align in patterns that have been approaching statistical inevitability for millions of years. The same circulation systems that have carried water vapor through cycles of clustering and dissipation now transport moisture concentrations so dense that the upper atmosphere reaches saturation levels unprecedented in planetary history. For the first time since Earth's formation, conditions exist for sustained precipitation, not the isolated droplet impacts that have characterized early water-rock interactions, but continuous rainfall that will persist for thousands of years without interruption. The meteorological processes that trigger this transition operate on scales that dwarf familiar weather systems. Atmospheric circulation cells that span continents begin to interact in ways that amplify moisture transport from the surface to high altitudes where cooling becomes most efficient. The planet's rapid rotation creates Coriolis effects that organize these circulation patterns into spiral systems that concentrate water vapor over regions where surface cooling has progressed furthest. These protostorm systems, while lacking the electrical activity and wind patterns of future hurricanes, achieve moisture concentrations that make sustained precipitation not merely possible but thermodynamically inevitable. The first drops of this extended rainfall begin to fall in regions where surface conditions have been optimized by millions of previous droplet impacts and pool formation cycles. Areas where repeated water-rock interactions have modified surface chemistry and thermal properties become preferential sites for droplet survival and accumulation. The same topographic features that have harbored temporary pools now serve as collection areas for the more sustained precipitation that characterizes true rainfall, creating geographic patterns that will influence hydrological development for millions of years. Temperature conditions during this epoch of first sustained rainfall remain extreme by any future standard. Surface temperatures still exceed 400 degrees Celsius in many regions, while atmospheric temperatures at altitudes where droplet formation occurs hover near the critical thresholds where liquid water becomes thermodynamically stable. The margin between conditions that support sustained precipitation and those that maintain the planet in its previous vapor-dominated state remains narrow, requiring precise balances between atmospheric cooling, surface heat dissipation, and circulation efficiency. Scientists estimate that the transition to sustained rainfall occurs when atmospheric water vapor concentrations reach critical densities, where droplet formation becomes a continuous rather than episodic process. Computer models suggest that this transition point occurs suddenly in geological terms, perhaps within a few thousand years, as positive feedback loops between droplet formation, surface cooling, and atmospheric circulation create cascading changes that amplify the initial shift towards sustained precipitation. Only took atmospheric physics a few millennia to discover that complex systems can exhibit threshold behaviors where gradual changes trigger sudden transitions. The physics governing sustained droplet formation in the extreme early atmosphere involves mechanisms that have no contemporary analogues. The combination of high atmospheric pressure, elevated temperatures, and complex chemical compositions creates conditions where droplet nucleation follows probability distributions that differ dramatically from those governing modern precipitation. Droplets form more readily but also evaporate more quickly, creating dynamic equilibria between formation and dissipation that maintain continuous precipitation despite thermal conditions that would seem prohibitive for liquid water persistence. Chemical interactions within falling raindrops become increasingly complex as atmospheric residence times increase and chemical concentrations build up through repeated evaporation and condensation cycles. Dissolved volcanic gases create acidic solutions that alter droplet behavior and surface interactions, while trace metals and sulfur compounds modify thermal properties in ways that can either enhance or inhibit droplet survival upon surface contact. These chemical modifications accumulate over the extended duration of sustained rainfall, creating precipitation that differs chemically from the relatively pure water that characterized earlier isolated droplet events. The acoustic signature of sustained rainfall creates Earth's first continuous weather-generated soundscape. Unlike the isolated hissing sounds produced by individual droplet impacts, sustained rainfall generates complex acoustic patterns that combine the sounds of droplets striking hot surfaces, steam generation from continuous evaporation, and the atmospheric turbulence created by large-scale circulation systems. These sounds propagate through the dense atmosphere with frequencies and intensities that create acoustic environments spanning vast geographic regions. Regional variations in rainfall intensity reflect the complex interplay between atmospheric circulation patterns and surface thermal conditions. Areas above particularly active volcanic regions experience reduced precipitation, as intense surface heating creates updrafts that disrupt droplet formation, while regions above cooler surface areas become focal points for enhanced rainfall as atmospheric stability promotes sustained droplet development. These geographic patterns in precipitation intensity begin to establish the first examples of regional climate differentiation on the planetary surface. The hydrological consequences of sustained rainfall manifest as the first continuous surface water flows in Earth's history. Unlike the brief connections between temporary pools that characterized earlier hydrological activity, Sustained rainfall creates stream flows that persist for seasons or years, carving the first erosional channels in cooling volcanic surfaces. These early streams follow topographic gradients established by volcanic processes, but their erosional action begins to modify surface topography in ways that will influence future drainage patterns for millions of years. Surface water accumulation during periods of sustained rainfall creates the first semi-permanent lakes in cooling volcanic basins. These early lakes differ dramatically from future freshwater or saltwater bodies. Their extreme temperatures, high mineral concentrations, and continuous thermal cycling between liquid and vapor phases create aquatic environments that have no modern analogues. Lake levels fluctuate constantly as evaporation competes with precipitation input, creating shoreline environments that experience repeated cycles of exposure and submersion. Modern climate models attempting to simulate sustained rainfall during this epoch must account for feedback mechanisms that operate across vastly different timescales. Precipitation affects surface cooling rates, which influence atmospheric circulation, which determines future precipitation patterns, creating coupled processes that can either stabilize or destabilize regional climate systems. The mathematical complexity of these feedback loops requires computational approaches that push beyond standard meteorological modeling techniques. The statistical distribution of rainfall events during this epoch follows patterns that reflect the underlying atmospheric processes governing droplet formation and circulation dynamics. Periods of intense precipitation alternate with intervals of reduced rainfall, as large-scale atmospheric patterns shift between configurations that favor and inhibit sustained droplet formation. The temporal patterns in precipitation intensity encode information about atmospheric circulation, efficiency, and surface thermal evolution that provides insights into planetary climate development. Chemical weathering processes accelerate dramatically under conditions of sustained rainfall on hot volcanic surfaces. The combination of acidic precipitation, high temperatures, and continuous water-rock contact creates weathering rates that exceed modern tropical conditions by orders of magnitude. These enhanced weathering processes extract minerals from volcanic rocks at unprecedented rates, creating chemical solutions that will eventually contribute to ocean salinity and atmospheric composition when permanent water bodies finally form. Atmospheric chemistry begins to change in response to sustained precipitation as continuous evaporation and condensation cycles concentrate and redistribute trace compounds throughout the atmospheric column. Some chemical species become concentrated in precipitation, while others remain preferentially in the vapor phase, creating chemical stratification patterns that influence atmospheric optical properties and heat transport efficiency. These chemical modifications to atmospheric composition represent some of the first examples of climate-driven atmospheric evolution. The geographic extent of sustained rainfall varies with large-scale atmospheric circulation patterns that shift over timescales ranging from years to millennia. During some periods, rainfall might cover continental-scale regions continuously for decades, while during other periods, precipitation becomes localized to smaller regions where specific combinations of atmospheric and surface conditions favor sustained droplet formation. These variations in precipitation geography create spatial patterns in surface modification and chemical weathering that establish regional differences in geological development. Energy balance calculations suggest that sustained rainfall represents a crucial phase transition in planetary thermal evolution, marking the point where atmospheric heat transport becomes efficient enough to maintain stable temperature gradients despite continued volcanic heating from the surface. The latent heat released by continuous condensation in the upper atmosphere creates thermal sinks that enhance radiative cooling to space, accelerating the overall planetary cooling process and creating positive feedback loops that favor continued precipitation. As thousands of years of sustained rainfall continue to modify surface conditions and atmospheric composition, the planet approaches another threshold, the point where surface cooling and precipitation intensity will allow the formation of permanent water bodies that persist despite seasonal variations in thermal input. Each year of continuous rainfall brings Earth closer to conditions where temporary lakes will become permanent seas, where seasonal streams will become perennial rivers, where the scattered pools and episodic flows of early hydrological activity will give way to integrated water systems that span continents and endure for geological ages. As the endless rain continues to fall across Earth's cooling surface, each droplet becomes an agent of chemical transformation. The water that strikes volcanic rock carries within its molecular structure the capacity to dissolve and transport mineral components that have remained locked in solid form since the planet's formation. This process of chemical weathering operates with unprecedented intensity under the extreme conditions of the early hydrological cycle, where acidic rainfall at temperatures approaching the boiling point of water interacts with fresh volcanic surfaces that have never before experienced sustained liquid contact. The chemistry of early rainwater differs dramatically from the relatively pure precipitation that will characterize later geological epochs. Dissolved atmospheric gases create solutions with pH levels that would classify as moderately acidic in modern terms, while trace concentrations of metals, sulfur compounds, and organic molecules produce chemical cocktails that have no contemporary analogues. Each raindrop functions as a microscopic chemical reactor, carrying dissolved atmospheric components into contact with mineral surfaces where rapid dissolution reactions extract elements that will eventually form the chemical foundation of future oceans. The process begins at the molecular level, as water molecules interact with the crystalline structure of cooling basalt. Silicon dioxide, the dominant component of volcanic rock, dissolves slowly even under these extreme conditions, releasing silicate ions that alter the chemical composition of surface water runoff. More readily soluble minerals, particularly those containing sodium, potassium, and magnesium, dissolve rapidly upon contact with hot acidic water, creating chemical solutions that become increasingly concentrated as water evaporates from heating surfaces. Ion oxidation produces some of the most dramatic chemical changes as water interacts with iron-rich volcanic minerals. The combination of dissolved oxygen from atmospheric sources and the elevated temperatures of early surface water creates conditions that promote rapid ion oxidation, producing ferric compounds that alter both the color and chemical properties of early surface water. These iron-rich solutions, ranging in color from yellow to deep red, create the first pigmented water bodies in Earth's history, while contributing dissolved metals that will eventually influence ocean chemistry for billions of years. Scientists puzzle over the precise reaction kinetics that govern mineral dissolution under the extreme conditions of early Earth surface water. Laboratory experiments can approximate the temperature and chemical conditions, but cannot replicate the complex interactions between atmospheric chemistry, surface heating, and the continuous cycling between liquid and vapor phases that characterizes early hydrological systems. Computer simulations suggest that reaction rates under these conditions might exceed modern weathering rates by factors of thousands, creating chemical flux rates that challenge conventional understanding of geochemical processes. Only took geochemistry 4 billion years to develop analytical techniques sensitive enough to detect the subtle isotopic signatures that preserve information about these ancient weathering processes in modern rock formations. The irony lies in studying Earth's most vigorous chemical reactions using the planet's most sophisticated instruments' mass spectrometers that can detect parts per billion concentrations of elements that were once dissolved in abundance by the first sustained rainfall to strike cooling volcanic surfaces. The geographic patterns of chemical weathering reflect the complex interplay between precipitation intensity, surface temperature, and rock composition across the cooling planetary surface. Regions that experience the most sustained rainfall develop the highest rates of mineral dissolution, creating chemical gradients that influence surface water composition on continental scales. Areas dominated by mafic volcanic rocks, rich in iron and magnesium, produce chemical solutions that differ dramatically from regions where more felsic compositions predominate, establishing regional variations in water chemistry that persist as surface water flows between different geological terrains. Evaporative concentration processes amplify the chemical evolution occurring in early surface water bodies. As water evaporates from heating lake surfaces, dissolved minerals become increasingly concentrated, eventually reaching saturation levels where precipitation of solid phases begins to occur. These evaporative cycles create the first examples of sedimentary mineral formation on Earth's surface, depositing layers of chemical precipitates that preserve records of early ocean chemistry in crystalline form. The temporal dynamics of chemical dissolution and concentration follow patterns that reflect both seasonal variations in precipitation and longer-term trends in surface cooling. During periods of intense rainfall, dilution effects reduce the concentration of dissolved minerals in surface water, while during drier intervals, evaporative concentration increases chemical concentrations to levels that can exceed modern seawater salinity by significant factors. These temporal variations in water chemistry create fluctuating chemical environments that drive continued mineral dissolution and precipitation cycles. Modern understanding of hydrothermal chemistry provides insights into the complex chemical processes occurring where early surface water interacts with hot volcanic rocks. The elevated temperatures create reaction conditions similar to those found in modern hydrothermal systems, promoting rapid mineral dissolution and the formation of complex chemical species that would be unstable under lower temperature conditions. These hydrothermal-like processes occurring at Earth's surface represent unique chemical environments that have no direct modern analogues. The role of atmospheric chemistry in controlling surface water composition becomes increasingly important as sustained rainfall continues to extract dissolved components from both rock surfaces and atmospheric sources. Carbon dioxide dissolution creates carbonic acid that enhances mineral dissolution rates while contributing carbonate species that will eventually form limestone deposits. Sulfur dioxide from volcanic sources creates sulfuric acid that produces even more aggressive chemical conditions for mineral dissolution, while also contributing sulfate ions that become major components of evolving ocean chemistry. Chemical gradients develop within individual water bodies as differential heating and evaporation rates create spatial variations in chemical concentration. Surface waters, exposed to direct solar heating experience enhanced evaporation that concentrates dissolved minerals, while deeper waters maintain more dilute chemical compositions. These chemical stratification patterns create density gradients that drive circulation within early lakes and seas, establishing the first examples of chemically driven fluid motion in terrestrial water bodies. The interaction between chemical weathering and physical erosion begins to reshape surface topography as chemically weakened rock becomes more susceptible to mechanical breakdown. Enhanced mineral dissolution creates rock surfaces with altered physical properties that experience accelerated erosion under the mechanical action of flowing water. This coupling between chemical and physical weathering processes creates erosion rates that exceed anything in Earth's future geological history, rapidly carving drainage networks that will guide surface water flow for millions of years. Biological implications of early ocean chemistry remain largely speculative, but the chemical conditions created by intensive mineral dissolution during this epoch establish many of the fundamental chemical properties that will eventually characterize life-supporting environments. The dissolution of phosphate minerals creates dissolved phosphorus that will become essential for biological energy storage, while the extraction of trace metals provides chemical elements that will serve as cofactors in future biochemical processes. Regional variations in volcanic rock composition create geographic patterns in water chemistry that establish chemical provinces with distinct characteristics. Areas dominated by ultramafic rocks produce water with high concentrations of magnesium and iron, while regions with more evolved volcanic compositions generate chemical solutions enriched in silica and alkali metals. These chemical provinces become increasingly distinct as continued weathering amplifies the initial differences in rock composition through preferential dissolution of specific mineral phases. The mass balance implications of intensive chemical weathering during this epoch are staggering when considered over geological timescales. The dissolution rates operating under these extreme conditions transfer enormous quantities of rock-derived chemicals into solution, creating chemical reservoirs that represent significant fractions of the total crustal inventory of many elements. These massive chemical transfers establish the geochemical cycling patterns that will govern ocean chemistry and atmospheric composition for billions of years into the future. As chemical weathering continues to operate at these unprecedented rates, surface water bodies develop chemical compositions that begin to resemble the saline solutions that will eventually characterize mature ocean systems. Each evaporation and concentration cycle increases the dissolved mineral content of surface waters, gradually approaching the chemical saturation levels where precipitation of evaporate minerals begins to occur. The transition from fresh rainwater to chemically evolved brines marks another crucial milestone in the chemical evolution that transforms a planet of cooling rock and water vapor into a world where complex chemical systems can support the eventual emergence of life. The accumulation of water across Earth's surface follows patterns dictated by gravity, topography, and the relentless geometry of cooling volcanic landscapes. Each raindrop that survives contact with the cooling surface joins a vast network of flows that seek the lowest available elevations, carving pathways through volcanic terrain that has never before experienced the sustained erosional action of liquid water. Over thousands of years of continuous precipitation, these individual flows converge and merge, creating the first integrated drainage systems that channel surface water toward the deepest basins where the planet's first true seas will eventually form. The physics governing surface water flow during this epoch operates under conditions that challenge conventional understanding of hydrology. Water temperatures that exceed 200 degrees Celsius in many regions create flow dynamics dominated by thermal expansion and convection currents that have no analog in modern river systems. Steam generation from the hottest surfaces creates atmospheric turbulence that influences flow patterns, while the extreme density of the early atmosphere affects how flowing water interacts with the air above it. These thermal and atmospheric effects produce flow behaviors that blur the boundary between liquid and vapor transport systems. Erosional processes accelerate dramatically as flowing water exploits weaknesses in volcanic rock that has been chemically altered by previous rainfall events. The combination of mechanical erosion from flowing water and chemical weathering from dissolved acids creates valley cutting rates that exceed modern geological processes by orders of magnitude. Stream channels that would require millions of years to form under current conditions carve their pathways through volcanic terrain in thousands of years, rapidly establishing drainage networks that will guide surface water flow long after thermal conditions moderate to more familiar ranges. The topographic inheritance from Earth's violent early history becomes apparent as surface water reveals and exploits structural features created by impact bombardment and volcanic processes. Ancient crater rims channel flows into circular drainage patterns that create the first examples of radial drainage systems, while linear features related to early tectonic activity guide stream flows along preferred orientations that reflect the planet's internal stress patterns. These structurally controlled drainage systems establish geographic frameworks that will influence continental-scale water distribution for billions of years. Scientists estimate that the transition from isolated surface water bodies to integrated drainage systems occurs over timescales of tens of thousands of years as continued precipitation and erosion gradually connect previously isolated basins through spillway development and channel head advancement. Computer models suggest that this integration process follows threshold behaviors where gradual changes in water levels trigger sudden connections between adjacent drainage basins, creating cascading effects that rapidly reorganize surface water distribution across continental scales. Only took geomorphology several thousand years to discover the fundamental principle that water flow creates the pathways that guide future water flow, establishing positive feedback loops that amplify initial topographic advantages into major drainage systems. The irony lies in Earth's first rivers being simultaneously the agents and the products of landscape evolution, carving their own channels while being constrained by the topographic frameworks they create through their erosional action. The chemical evolution of flowing surface water creates geographic patterns in water composition that reflect both the lithologic diversity of volcanic terrains and the variable residence times that characterize different flow pathways. Water that travels rapidly through steep channels maintains chemical compositions similar to initial rainfall chemistry, while water that moves slowly through low-gradient systems experiences extended contact with rock surfaces that dramatically increases dissolved mineral concentrations. These flow path-dependent chemical variations create the first examples of geographic diversity in terrestrial water chemistry. Sediment transport processes begin to operate for the first time in Earth's history as flowing water acquires the capacity to erode, transport, and deposit solid particles derived from mechanical and chemical breakdown of volcanic rocks. The extreme temperatures and chemical conditions create sediment loads that differ dramatically from modern river systems. Particles range from chemically unaltered volcanic fragments to complex precipitates formed through evaporative concentration of dissolved minerals. These early sediment systems establish the first examples of clastic sedimentation, while simultaneously depositing chemical precipitates that record the evolving chemistry of early surface water. Hydraulic geometry relationships that govern the dimensions and flow characteristics of early stream channels operate under thermal and chemical conditions that push beyond the ranges where modern river equations remain valid. Channel widths, depths, and slopes adjust to accommodate flows that experience continuous thermal cycling between liquid and vapor phases, creating channel geometries that reflect the unique physics governing hot water flow through volcanic landscapes. These early channels establish morphological templates that will influence drainage system evolution long after thermal conditions moderate. The acoustic environment created by flowing surface water generates Earth's first examples of river sounds, the continuous murmur of water moving through rock channels, punctuated by the hissing and bubbling sounds created when flowing water encounters particularly hot surfaces. These sounds propagate through the dense early atmosphere with frequencies and intensities that create acoustic landscapes spanning entire drainage basins, establishing the first examples of geographically extensive natural soundscapes. Confluence dynamics, where tributary streams join larger flows, create complex mixing zones where waters with different thermal histories and chemical compositions interact. These mixing processes produce chemical reactions and thermal adjustments that affect flow properties downstream from confluences, creating longitudinal variations in water chemistry and temperature that reflect the cumulative inputs from multiple tributary systems. Early confluence zones become sites of enhanced chemical activity where mineral precipitation and dissolution processes operate with particular intensity. Modern understanding of river network topology provides frameworks for analyzing how early drainage systems achieve the geometric efficiency that characterizes mature river networks. The principles governing drainage density, stream ordering, and network connectivity operate even under the extreme conditions of early Earth surface water flow, creating network geometries that optimize water transport efficiency despite the thermal and chemical complications that characterize early hydrological systems. The interaction between surface water flow and volcanic activity creates complex feedback relationships that influence both hydrological and geological processes. Flowing water enhances cooling of volcanic surfaces through thermal transfer, potentially affecting eruption patterns and lava flow behavior. Conversely, volcanic activity can disrupt established drainage patterns, creating temporary lakes and redirecting surface flows in ways that reorganize regional hydrology. These interactions between surface water and volcanic processes create coupled Earth system behaviors that have no modern analogues. Seasonal variations in precipitation intensity drive corresponding changes in surface water flow that create the first examples of hydrological seasonality on Earth's surface. During periods of enhanced rainfall, stream flows increase dramatically, expanding channel dimensions and accelerating erosional processes. During drier intervals, reduced flows concentrate in the deepest channels, while exposing previously submerged surfaces to enhanced thermal input from the atmosphere and underlying rock. These seasonal flow variations create temporal patterns in erosion and chemical weathering that influence landscape evolution. The geographic distribution of surface water convergence zones begins to establish patterns that will eventually determine the locations of major ocean basins. Areas where large drainage systems converge create sites of maximum water accumulation that experience enhanced erosional excavation and rapid sediment deposition. These convergence zones become focal points for continued topographic modification that gradually transforms shallow drainage confluences into deep basins capable of containing large volumes of surface water. Statistical analysis of early drainage network development reveals scaling relationships that connect small-scale erosional processes with large-scale landscape evolution. The fractal geometry that characterizes mature river networks emerges even during these early stages of drainage development, suggesting that the mathematical principles governing network topology operate independently of the specific thermal and chemical conditions that characterize different geological epochs. As thousands of years of surface water flow continue to carve deeper channels and extend drainage networks across the cooling planetary surface, the stage prepares for a transition from temporary water accumulation to permanent water storage. The same erosional processes that create integrated drainage systems also excavate the deep basins where surface water will eventually accumulate in volumes sufficient to create Earth's first permanent seas. Bodies of water that will persist through seasonal variations in precipitation and begin the transition from a planet where water temporarily visits the surface to a world where water permanently resides in oceanic reservoirs that will endure for geological ages. The planet breathes with water for the first time, after millions of years of unidirectional atmospheric circulation that carried water vapor from the molten surface to the cooling heights above. Earth develops the first recognizable water cycle, a planetary circulation system where water moves continuously between atmospheric, surface, and subsurface reservoirs in patterns that will persist, with modifications, for the remainder of planetary history. This emergence of cyclical water movement marks a fundamental transition from linear atmospheric processes to integrated hydrological systems that connect every part of the planet's surface with every region of its atmosphere. The physics governing this early water cycle operates under thermal and chemical conditions that create circulation patterns unlike anything in Earth's future climate history. Evaporation from surface water bodies occurs at rates that exceed modern tropical conditions by orders of magnitude, driven by surface temperatures that maintain liquid water near its boiling point despite atmospheric pressures that elevate boiling temperatures well above standard values. This intense evaporation creates atmospheric moisture concentrations that approach saturation levels throughout much of the atmospheric column, establishing conditions where condensation and precipitation become continuous rather than episodic processes. Atmospheric transport of water vapor follows circulation patterns driven by the same convection systems that have dominated early atmospheric dynamics, but now modified by the presence of surface water bodies that serve as both sources and sinks for atmospheric moisture. Large-scale circulation cells transport water vapor from regions of net evaporation to areas where atmospheric cooling promotes enhanced precipitation, creating geographic patterns in water cycle intensity that reflect both thermal and topographic influences on atmospheric circulation. These early atmospheric transport systems establish the first examples of regional climate differentiation based on hydrological processes. The chemical dimension of early water cycling adds complexity absent from purely physical circulation systems. Water that evaporates from surface bodies carries dissolved chemicals into the atmosphere, where they participate in chemical reactions that alter both atmospheric composition and the properties of water that eventually returns to the surface through precipitation. Evaporative concentration processes in surface water bodies increase dissolved mineral concentrations, while atmospheric chemical processing can either enhance or reduce the chemical content of precipitation, creating cycling patterns that transport dissolved materials between surface and atmospheric reservoirs. Scientists puzzle over the precise mechanisms that govern chemical transport in early atmospheric water cycling systems. The extreme temperatures and chemical compositions create conditions where standard models of evaporation and condensation behavior require significant modifications to account for the interactions between water vapor and dissolved chemical species. Computer simulations suggest that chemical cycling during this epoch might operate according to principles that differ fundamentally from those governing modern atmospheric chemistry, requiring new theoretical frameworks that can accommodate the coupled thermal and chemical processes characteristic of early Earth conditions. Only took planetary science a century to recognize that water cycles represent Earth system processes that couple atmospheric, hydrological, and geochemical systems in ways that cannot be understood through study of individual components alone. The irony lies in early Earth's water cycle being simultaneously simpler and more complex than modern systems. Simpler in terms of the limited geographic extent of surface water bodies, but more complex due to the extreme thermal and chemical conditions that create coupling mechanisms absent from contemporary hydrological systems. The temporal dynamics of early water cycling exhibit periodicities that reflect both atmospheric circulation patterns and the thermal evolution of surface water bodies. Daily cycles in solar heating create diurnal variations in evaporation rates that drive corresponding changes in atmospheric moisture content and precipitation intensity. Longer-term cycles related to seasonal variations in solar input and volcanic activity create periodic variations in water cycle intensity that span timescales from weeks to years, establishing the first examples of climate variability driven by hydrological processes. Regional variations in water cycle intensity create geographic patterns in surface water distribution that begin to establish stable climatic zones with characteristic hydrological properties. Areas where atmospheric circulation patterns favor net moisture transport develop enhanced precipitation rates that support larger surface water bodies and more intense chemical weathering processes. Regions where circulation patterns promote net moisture, export experience, reduced precipitation, and enhanced evaporative concentration, creating more saline surface water bodies with distinct chemical signatures. The energy balance implications of early water cycling represent a crucial component in planetary thermal evolution during this epoch. Latent heat transport through evaporation and condensation processes becomes a major mechanism for heat transfer from the surface to atmospheric levels, where radiative cooling can effectively remove thermal energy from the planetary system. This enhanced cooling efficiency accelerates the overall planetary cooling process, while simultaneously stabilizing atmospheric thermal structure in ways that promote continued water cycle operation. Modern understanding of atmospheric water vapor feedback mechanisms provides insights into the stability characteristics of early water cycling systems. The relationships between surface temperature, atmospheric moisture content, and precipitation efficiency create feedback loops that can either stabilize or destabilize water cycle operation depending on the specific thermal and chemical conditions involved. Mathematical analysis suggests that early water cycles might have exhibited threshold behaviors where small changes in surface conditions could trigger large-scale reorganizations of atmospheric circulation patterns. The interaction between water cycling and surface geological processes creates coupled Earth system behaviors that influence both hydrological and geological evolution. Enhanced chemical weathering, driven by intense water cycling, accelerates the transfer of rock-derived chemicals to surface water bodies, altering both surface water chemistry and the chemical composition of materials available for atmospheric transport. Erosional processes enhanced by vigorous water cycling modify surface topography in ways that influence atmospheric circulation patterns and regional water distribution. Atmospheric circulation efficiency improves as water cycling systems develop, creating more effective heat transport mechanisms that enhance planetary cooling rates. The three-dimensional circulation patterns that transport water vapor between surface and atmospheric reservoirs also transport thermal energy, creating atmospheric heat engines that operate with efficiencies determined by the temperature differences between surface evaporation sites and high-altitude condensation regions. These atmospheric heat engines represent some of the most effective planetary cooling mechanisms operating during this epoch. The chemical evolution of atmospheric composition accelerates as water cycling systems transport reactive chemical species between surface and atmospheric reservoirs, where they can participate in chemical reactions impossible under purely surface or purely atmospheric conditions. Dissolved atmospheric gases concentrate in surface water bodies through evaporative processes, while surface-derived chemicals enter atmospheric chemistry through evaporative transport, creating chemical cycling systems that couple atmospheric and surface chemical evolution. Hydrological residence times in different components of the early water cycle system vary dramatically depending on the specific pathways involved in water transport between reservoirs. Water in small surface pools might complete evaporation-condensation cycles in hours, while water in larger surface bodies might remain in surface reservoirs for months or years before entering atmospheric circulation. These variable residence times create chemical fractionation effects that produce geographic variations in water chemistry, reflecting the different cycling pathways water follows through the early hydrological system. The stability of early water cycling systems depends critically on maintaining thermal conditions that support both liquid water persistence at the surface and efficient atmospheric moisture transport at altitude. Surface temperatures must remain low enough to prevent complete water evaporation while staying high enough to drive vigorous evaporation rates. while atmospheric temperatures must provide sufficient cooling at altitude to maintain condensation and precipitation processes. These thermal constraints define narrow operating windows where stable water cycling becomes possible. Statistical analysis of early water cycle variability reveals patterns that reflect the underlying atmospheric and thermal processes governing system operation. Fluctuations in evaporation rates, precipitation intensity, and atmospheric moisture content follow probability distributions that encode information about the efficiency and stability of early hydrological systems. These statistical signatures provide quantitative measures of how water cycle systems respond to variations in external forcing and internal system dynamics. As early water cycling systems continue to operate and evolve over thousands of years, they gradually modify both atmospheric and surface conditions in ways that enhance their own stability and efficiency. Enhanced atmospheric moisture transport improves cooling efficiency, which reduces surface temperatures, which allows larger surface water bodies to persist, which increases evaporation rates, which enhances atmospheric moisture transport. These positive feedback loops create self-reinforcing cycles that drive the early water cycle system toward increasingly stable and effective operation, setting the stage for the permanent establishment of oceanic water bodies that will maintain hydrological cycling for billions of years into the future. In the warm margins where land meets the earliest seas, chemistry conducts its first experiments with complexity. The rhythmic rise and fall of water levels creates zones of repeated wetting and drying that concentrate dissolved organic compounds in ways impossible in either purely aquatic or purely terrestrial environments. These tidal margins, heated by residual volcanic warmth and stirred by primitive tidal forces, become natural laboratories where the molecular building blocks of life accumulate and interact under conditions that will never again exist in Earth's history. The chemistry occurring in these early tidal pools operates under thermal conditions that push organic molecules toward energy states and reaction pathways unavailable under more moderate temperatures. Amino acids, formed through atmospheric chemical processes and delivered to the surface through rainfall, concentrate in evaporating pools where elevated temperatures and mineral catalysts promote peptide bond formation. Simple sugars, created through interactions between atmospheric carbon compounds and volcanic mineral surfaces, undergo thermal cycling that drives the formation of more complex carbohydrates that can persist in hot water environments. The physics of molecular concentration in repeatedly evaporating pools creates chemical environments that concentrate organic compounds to levels that exceed typical cellular concentrations in modern organisms. As water evaporates from heating pool surfaces, dissolved organic molecules become increasingly concentrated, eventually reaching supersaturation levels where crystallization and precipitation begin to occur. These concentration processes, driven by thermal cycling rather than biological activity, create the first examples of complex organic chemistry operating at concentrations approaching those found in living systems. Scientists theorize that the repeated thermal cycling characteristic of early tidal environments might have provided the energy sources necessary for driving chemical reactions that would be thermodynamically unfavorable under isothermal conditions. The temperature fluctuations experienced by organic molecules in pools that heat during low water periods and cool during high water intervals create thermal gradients that can drive chemical reactions uphill from thermodynamic equilibrium, potentially enabling the formation of complex molecular structures that would spontaneously decompose under constant temperature conditions. Only took biochemistry 4 billion years to recognize that the molecular complexity characteristic of living systems might have emerged through purely chemical processes operating under conditions that no longer exist on Earth's surface. The irony lies in studying the origins of life's chemistry using organisms whose molecular machinery operates under thermal conditions that would have destroyed the earliest organic molecules, requiring extrapolation backward through billions of years of evolutionary optimization to imagine chemistry operating without cellular control mechanisms. The mineral surfaces present in early tidal environments serve as catalytic substrates that promote organic chemical reactions through mechanisms that remain poorly understood despite decades of laboratory research. Iron and sulfur compounds, abundant in volcanic rocks and concentrated through chemical weathering processes, provide electron transfer capabilities that facilitate organic synthesis reactions. Clay minerals, formed through the chemical alteration of volcanic ash in hot water environments, create surface chemistry environments that can template the formation of more complex organic polymers from simple precursor molecules. Chemical gradients develop within individual tidal pools as differential heating and evaporation create spatial variations in temperature, concentration, and pH that drive chemical transport and reaction processes. Organic molecules migrate through these chemical gradients in response to solubility changes and chemical potential differences, creating dynamic chemical systems where molecular transport couples with chemical synthesis to produce complex spatial patterns in organic chemistry. These gradient-driven processes represent some of the earliest examples of chemical self-organization operating in terrestrial environments. The temporal dynamics of organic chemical evolution in tidal pools follow patterns that reflect both tidal cycling and longer-term trends in surface cooling and chemical evolution. Daily or seasonal variations in water level drive repeated concentration and dilution cycles that subject organic molecules to thermal and chemical stress tests that select for molecular structures capable of surviving thermal cycling. Longer-term evolution in pool chemistry, driven by continued chemical weathering and atmospheric evolution, gradually changes the chemical environments where organic synthesis occurs. Modern understanding of prebiotic chemistry provides frameworks for analyzing the types of organic reactions that might have occurred in early tidal environments. But the extreme thermal and chemical conditions create uncertainty about which specific pathways would have been kinetically favored under early Earth conditions. Laboratory experiments can replicate some aspects of early tidal chemistry, but cannot duplicate the complex interactions between thermal cycling, mineral catalysis, and chemical concentration that characterize natural early Earth environments. The role of phosphorus availability in early organic chemistry becomes crucial when considering the formation of energy storage molecules that will eventually become central to biological systems. Phosphate minerals, dissolved through chemical weathering of volcanic rocks, concentrate in evaporating tidal pools where they can participate in phosphorylation reactions that create high-energy phosphate bonds. These early examples of phosphorylation chemistry occur through purely chemical mechanisms, but establish the chemical precedents for the energy storage systems that will later characterize biological metabolism. Chemical diversity in early tidal pools reflects both the variety of organic precursors delivered through atmospheric processes and the range of reaction conditions created by thermal and chemical gradients within pool environments. Different regions of the same pool might experience chemical conditions that favor different types of organic synthesis, creating chemical microenvironments where distinct families of organic compounds can form and persist. This chemical heterogeneity within individual pools creates opportunities for chemical interactions between different classes of organic molecules. The interaction between organic chemistry and mineral precipitation processes creates hybrid chemical systems where organic molecules become incorporated into mineral structures, while mineral surfaces template organic polymer formation. These organic-mineral interactions produce chemical entities that combine the stability of mineral structures with the functional complexity of organic molecules, creating the first examples of composite materials that exhibit both geological and chemical properties. Chirality effects begin to appear in organic synthesis reactions occurring in early tidal environments, as asymmetric mineral surfaces and circularly polarized radiation from atmospheric scattering processes create chemical environments that preferentially synthesize organic molecules with specific stereochemical configurations. These early examples of chiral selection establish molecular handedness preferences that will eventually become universal characteristics of biological chemistry, suggesting that the stereochemical properties of life might reflect chemical constraints operating in early tidal environments. The energy budget implications of organic synthesis in early tidal pools remain poorly constrained but potentially significant for understanding how chemical complexity can emerge in the absence of biological energy management systems. Thermal energy from surface heating, chemical energy from mineral-organic interactions, and electromagnetic energy from solar radiation all contribute to driving organic synthesis reactions, creating multiple energy sources that can support chemical complexity even in the absence of the sophisticated energy management systems characteristic of living organisms. Statistical analysis of organic chemical diversity in simulated early tidal environments reveals patterns that suggest emergent organizational principles operating in complex chemical systems. The distribution of molecular sizes, the frequency of specific chemical functional groups, and the connectivity patterns in organic polymers follow mathematical relationships that hint at chemical self-organization processes that concentrate molecular complexity in specific size ranges and structural configurations. Chemical inheritance mechanisms begin to operate in early tidal pools as organic molecules that form under specific chemical conditions influence the chemical environments where subsequent synthesis occurs. Molecules that enhance their own formation through catalytic activity or template effects create positive feedback loops that increase their own abundance, establishing the first examples of chemical systems that exhibit properties analogous to replication and selection. These chemical inheritance processes represent stepping stones toward the more sophisticated inheritance mechanisms that will eventually characterize biological systems. The geographic distribution of chemical complexity in early tidal environments reflects the spatial patterns in thermal conditions, mineral availability, and organic precursor delivery that characterize different coastal regions. Some tidal areas develop particularly favorable combinations of chemical conditions that support enhanced organic synthesis, while others remain dominated by simpler chemical systems. These geographic variations in chemical complexity establish spatial patterns that might influence where the transition from chemical complexity to biological organization eventually occurs. As thermal conditions continue to moderate and chemical evolution continues to operate in countless tidal pools scattered across Earth's emerging coastlines, the molecular foundations for biological complexity accumulate through processes that remain purely chemical but increasingly approach the organizational thresholds where chemistry begins to exhibit the properties that will eventually characterize living systems. Each cycle of concentration and dilution, each thermal stress test, each molecular interaction in these early chemical laboratories contributes to building the molecular inventory that will eventually support the emergence of self-replicating chemical systems capable of Darwinian evolution. Across the vast expanses of cooling planetary surface, water spreads with the quiet inevitability of gravity and time. The isolated seas that began as temporary accumulations in volcanic depressions now connect through spillways and overflows, creating the first continuous water bodies that span distances measured in hundreds of kilometers rather than meters. These early oceanic expanses, still hot enough to generate steam at their surfaces and chemically concentrated beyond any modern analog, represent the first truly permanent reservoirs of liquid water in Earth's history, bodies of water that will persist through seasonal variations in temperature and precipitation to become stable features of planetary geography. The thermal structure of these early oceans defies comparison with any modern aquatic environment. Surface temperatures approach 80 degrees Celsius in the coolest regions, while deeper waters maintain temperatures that exceed 100 degrees Celsius, remaining liquid only due to the extreme atmospheric pressure that elevates boiling points well above standard values. Thermal stratification patterns develop as heat from the volcanic sea floor creates convection currents that transport the hottest water toward the surface, where atmospheric cooling and evaporation remove thermal energy at rates that begin to balance geothermal input from below. The chemistry evolving within these early oceanic systems creates solutions that concentrate dissolved minerals to levels that approach saturation for multiple chemical species simultaneously. Sodium and chloride ions, extracted from volcanic rocks through intensive chemical weathering, accumulate to concentrations that exceed modern seawater salinity by significant factors. Iron compounds, dissolved from mafic volcanic sources, create oceanic chemistry dominated by reduced metal species that will not persist once atmospheric oxygen becomes available. Sulfur compounds from volcanic outgassing create acidic conditions that enhance mineral dissolution while contributing sulfate ions that become major components of early ocean chemistry. Scientists estimate that the transition from isolated water bodies to continuous oceanic coverage occurs over timescales of hundreds of thousands of years, as continued precipitation and spillway development gradually connect previously separate basins into integrated aquatic systems. Computer models suggest that this oceanic integration follows threshold behaviors where rising water levels in individual basins trigger sudden connections that rapidly redistribute water across continental scale regions, creating oceanic coverage patterns that reflect both topographic constraints and hydrological overflow dynamics. Only took hydrology several 100,000 years to discover that ocean formation represents a phase transition in planetary water distribution, where isolated water storage gives way to integrated aquatic systems that span continental distances. The irony lies in Earth's first oceans being simultaneously more extreme and more stable than any future oceanic system, more extreme due to their thermal and chemical conditions, but more stable due to their enormous thermal mass that resists rapid temperature changes. The circulation patterns developing within early oceanic systems create the first examples of large-scale aquatic fluid motion driven by combinations of thermal, chemical, and gravitational forces. Density differences created by temperature and salinity variations drive convection patterns that transport water through three-dimensional circulation cells spanning entire ocean basins. These early oceanic circulation systems lack the wind-driven components that will later dominate ocean dynamics. Instead, operating as purely thermal and chemical convection systems that transport heat, dissolved chemicals, and suspended materials across oceanic distances. Tidal forces from the nearby moon create the first oceanic tidal systems. Though the extreme atmospheric density and unusual oceanic chemistry produce tidal behaviors that differ dramatically from familiar tidal patterns, the gravitational pull that will later create modest sea level variations instead generates massive internal waves that propagate through the density-stratified early oceans, creating subsurface turbulence that enhances mixing between oceanic layers while contributing to the complex circulation patterns that characterize early oceanic dynamics. The acoustic environment within early oceanic systems creates underwater soundscapes, unlike anything in Earth's future marine environments. Thermal convection generates low-frequency rumbles that propagate through hot, dense water with acoustic properties dramatically different from modern seawater. Bubble formation from dissolved gases creates high-frequency acoustic noise, while the interaction between internal waves and seafloor topography produces complex acoustic interference patterns that create underwater acoustic environments spanning oceanic basins. Chemical precipitation processes begin to operate within early oceanic systems as dissolved mineral concentrations approach saturation levels for various chemical species. Evaporative concentration at ocean surfaces creates supersaturated surface waters that precipitate salt crystals, creating the first examples of marine evaporate formation. Chemical reactions between different dissolved species produce precipitates that settle toward the seafloor, creating the first oceanic sediments composed of chemical precipitates rather than mechanical erosion products. Modern understanding of ocean formation processes provides frameworks for analyzing how early oceanic systems achieve the chemical and thermal equilibria that allow stable oceanic persistence despite extreme environmental conditions. The balance between chemical input from weathering processes, thermal input from geothermal sources, and energy loss through evaporation and atmospheric cooling creates steady-state conditions that can maintain oceanic systems even under thermal conditions that would seem prohibitive for stable water body persistence. The biological implications of early oceanic chemistry remain largely speculative, but the chemical conditions developing within these early ocean systems begin to approach ranges where complex chemical processes might operate with sufficient stability to support chemical evolution toward biological organization. The thermal energy available in early oceanic systems provides abundant energy sources for driving chemical reactions, while the chemical diversity created by intensive mineral dissolution provides raw materials for complex chemical synthesis. Geographic variations in early oceanic chemistry reflect both regional differences in volcanic rock composition and the variable circulation patterns that transport dissolved chemicals between different oceanic regions. Some oceanic areas develop chemical compositions dominated by mafic mineral dissolution, while others reflect more felsic source compositions, creating oceanic chemical provinces with distinct characteristics. These chemical variations establish geographic patterns that influence both chemical and physical oceanic processes. The energy balance implications of early oceanic systems represent crucial components in planetary thermal evolution as oceanic thermal mass begins to dominate planetary heat storage. The enormous thermal capacity of oceanic water bodies creates thermal buffers that moderate surface temperature variations while storing geothermal energy that can be released over extended time periods. This oceanic thermal regulation begins to stabilize planetary surface temperatures in ways that promote continued oceanic persistence. Evaporative water loss from early oceanic surfaces creates atmospheric moisture transport that influences precipitation patterns across continental regions adjacent to oceanic systems. Enhanced evaporation from hot oceanic surfaces increases atmospheric moisture content, promoting enhanced precipitation in coastal regions while creating circulation patterns that transport oceanic moisture to continental interiors. These oceanic atmospheric coupling mechanisms establish the first examples of oceanic influence on continental climate patterns. The temporal evolution of early oceanic systems follows patterns that reflect both internal oceanic processes and external forcing from continued planetary cooling and atmospheric evolution. Oceanic temperatures gradually decrease as planetary cooling reduces geothermal input while atmospheric evolution enhances radiative cooling efficiency. Chemical evolution continues as weathering processes add dissolved materials while precipitation processes remove others, creating oceanic chemistry that evolves toward compositions that will eventually support biological processes. Statistical analysis of early oceanic variability reveals patterns that reflect the complex interactions between thermal, chemical, and circulation processes that govern oceanic system behavior. Fluctuations in oceanic temperature, chemistry, and circulation exhibit scaling relationships that encode information about the underlying physical processes governing oceanic dynamics, providing quantitative measures of how oceanic systems respond to external forcing and internal feedback mechanisms. Sedimentary processes begin to operate within early oceanic systems as chemical precipitation and mechanical erosion combine to create the first oceanic sediment accumulations. Chemical precipitates settle through the water column to create seafloor deposits of evaporites and metal oxides, while erosional products from continental weathering create clastic sediments that preserve records of early continental geology. These early oceanic sediments establish the first marine sedimentary systems that will eventually preserve detailed records of oceanic and atmospheric evolution. As early oceanic systems continue to expand and evolve over hundreds of thousands of years, they gradually approach chemical and thermal conditions that will eventually support the complex chemistry required for biological organization. Each degree of cooling, each chemical modification, each circulation pattern adjustment brings early oceanic chemistry closer to the ranges where chemical evolution can operate with sufficient efficiency to support the emergence of self-replicating chemical systems. The blue waters that spread across the cooling planet carry within their chemical complexity the potential for life processes that remain millions of years in the future, but whose chemical foundations accumulate steadily in oceanic systems that have achieved the stability and complexity necessary to support the next phase of planetary evolution. Through cycles that span millions of years, the same water molecules that first condensed in the cooling atmosphere above a molten world continue their endless circulation between sea and sky. Each drop that falls as rain today carries within its molecular structure the memory of countless previous journeys from the superheated steam that once filled Earth's early atmosphere, through the first tentative clustering events in the cooling heights above volcanic landscapes, down through the historic first contacts with cooling stone, and into the chemical laboratories of early tidal pools where molecular complexity first began to approach the thresholds of biological organization. The water cycle that now operates across the blue planet exhibits fundamental patterns established during those first eons of atmospheric and oceanic development. The same circulation systems that once carried water vapor through vertical journeys spanning the full height of the early atmosphere now transport moisture between ocean surfaces and continental precipitation in patterns that preserve the geographic relationships between thermal energy, atmospheric circulation, and water distribution established when the planet first learned to breathe with water. Modern rain falls through atmospheric conditions that would seem impossibly cool and thin to water molecules that experienced their first condensation in the dense, superheated atmosphere of early Earth. Yet, the physics governing droplet formation, the chemistry driving cloud development, and the circulation patterns that transport atmospheric moisture remain fundamentally unchanged from the processes that operated when water first began its transition from vapor to liquid in the cooling sky above a world of molten rock. The oceans that now cover most of Earth's surface maintain chemical compositions that preserve signatures of the intensive mineral dissolution that occurred when hot rain first contacted cooling volcanic rocks. Dissolved sodium and chloride ions that create modern seawater salinity represent the accumulated products of chemical weathering processes that operated with unprecedented intensity during the early epochs of sustained rainfall. Trace elements that serve as micronutrients for modern marine life were first extracted from volcanic minerals by the acidic precipitation that fell on cooling basalt surfaces billions of years ago. Scientists recognize in modern atmospheric circulation patterns the descendants of the convection systems that first transported water vapor from molten surface areas to the cooling altitudes where condensation became possible. The geographic distribution of modern precipitation reflects topographic features carved by erosional processes that operated when flowing water first acquired the capacity to modify planetary surface topography through mechanical and chemical weathering of volcanic terrains. Only took Earth 4 billion years to establish hydrological systems complex enough to support the emergence and evolution of biological organization that can study its own planetary origins. The irony lies in living organisms composed primarily of water using their biochemical machinery to investigate the deep history of the water molecules that constitute their own cellular structure, creating a kind of planetary self-awareness where Earth's early water history becomes accessible to inquiry through the agency of biological systems that water itself made possible. The chemical complexity that now characterizes biological systems preserves organizational principles that first emerged in the purely chemical environments of early tidal pools, where organic synthesis occurred through thermal cycling and mineral catalysis. The amino acids that form proteins in modern cells represent chemical structures whose synthesis pathways were first established through the thermal and chemical processes that operated in hot water environments that no longer exist on Earth's surface. Atmospheric moisture transport systems continue to operate according to energy balance principles established when the early atmosphere first developed efficient mechanisms for transporting thermal energy from surface heating to high-altitude cooling zones, where radiative heat loss could effectively reduce planetary temperatures. Modern weather systems represent the evolutionary descendants of the atmospheric circulation patterns that first enabled sustained precipitation on a cooling world. The residence times that characterize water molecules in different components of the modern hydrological cycle preserve statistical signatures of the circulation timescales that operated when atmospheric and oceanic water cycling first achieved stable operation. Water molecules that spend decades in oceanic circulation before returning to atmospheric transport follow pathways established by the thermal and chemical gradients that drove early oceanic circulation systems through convection patterns spanning entire ocean basins. Geological records preserved in ancient rock formations encode information about the chemical and thermal conditions that characterized water cycling during Earth's earliest hydrological epochs. Isotopic signatures in mineral deposits preserve evidence of the extreme temperatures and chemical concentrations that characterized early precipitation and surface water chemistry, providing quantitative constraints on the environmental conditions under which Earth's hydrological systems first developed stable operation. Modern climate systems operate through feedback mechanisms that first emerged when atmospheric water vapor, surface heating, and circulation efficiency achieved the coupled relationships necessary to maintain stable water cycling despite external perturbations. The sensitivity of modern climate to changes in atmospheric composition reflects the delicate balance requirements that have characterized Earth's hydrological systems since water first achieved stable circulation between atmospheric and surface reservoirs. The biological significance of water extends beyond its role as a chemical solvent to encompass its function as the medium through which planetary-scale chemical cycling operates. The carbon, nitrogen, phosphorus, and sulfur cycles that support modern biological productivity represent chemical transport systems that operate through hydrological mechanisms first established when water cycling began to connect atmospheric, oceanic, and terrestrial chemical reservoirs. Tidal processes that now drive coastal ecosystems and influence global oceanic circulation patterns represent the mature expression of gravitational effects that first created water level variations in early oceanic systems. The twice-daily tidal cycling that characterizes modern coastal environments preserves the temporal patterns established when lunar gravitational forces first began to influence oceanic water distribution on a planet where surface water had achieved sufficient depth and geographic extent to respond to celestial mechanics. The acoustic environments created by modern hydrological systems, the sounds of rivers, rainfall, and ocean waves, represent the evolutionary descendants of the first water-generated sounds that accompanied droplet impact, stream flow, and oceanic circulation in early aquatic systems. These natural soundscapes preserve acoustic signatures of the fundamental physical processes that govern water behavior under gravitational and thermal forcing. Chemical weathering processes that continue to shape continental landscapes operate through mechanisms first established when acidic early precipitation began dissolving minerals from volcanic rock surfaces. The chemical composition of modern river water reflects the cumulative operation of chemical weathering processes that have operated continuously since water first achieved sustained contact with solid rock surfaces, creating chemical flux patterns that connect continental geology with oceanic chemistry. Evolutionary processes that have shaped the biochemical machinery of modern life reflect the chemical constraints and opportunities that characterized early aquatic environments, where biological organization first emerged from purely chemical complexity. The molecular structures that enable modern cellular metabolism preserve chemical solutions to thermodynamic problems that first arose in the hot, chemically concentrated environments of early oceanic and tidal systems. Statistical analysis of modern hydrological variability reveals scaling relationships that preserve information about the fundamental physical processes governing water cycling under Earth's gravitational and thermal conditions. These mathematical patterns connect modern climate variability with the atmospheric and oceanic circulation patterns that first achieved stable operation when Earth developed integrated hydrological systems spanning global scales. The water that falls as gentle rain through cool modern atmospheres carries within its circulation history the complete record of planetary evolution from molten rock to living world. Each molecule preserves in its chemical bonds the energy relationships established when water first achieved liquid existence, while participating in circulation patterns that connect every part of Earth's surface with every region of its atmosphere through hydrological processes that operate with efficiency and stability, achieved through billions of years of evolutionary optimization. In the quiet persistence of modern rainfall, in the vast circulation of oceanic currents, in the daily rise and fall of tidal waters, the same patient water continues the planetary breathing that began when Earth first learned to balance thermal energy input with radiative cooling through the agency of atmospheric moisture transport. The rain still falls, as it has fallen for billions of years, carrying the memory of planetary origins while enabling the continued operation of hydrological systems that connect the deep history of Earth's cooling with the ongoing evolution of atmospheric, oceanic, and biological complexity that defines our living world. The ancient rhythms slow towards stillness. Across the blue expanses that now cover most of Earth's surface, the same water molecules that once existed only as superheated steam continue their eternal circulation with the quiet patience of deep time. Each wave that breaks against a distant shore carries within its motion the memory of the first droplets that survived contact with cooling stone. Each cloud that drifts through cool modern skies preserves the organizing principles first established when atmospheric clustering began in the harsh chemistry of early Earth's dense atmosphere. In laboratories around the world, scientists examine microscopic bubbles trapped in ancient rocks, finding within them samples of Earth's earliest atmosphere, evidence of the steam-filled sky that existed when water first began its transition from vapor to liquid. These tiny inclusions preserve actual molecules from the epoch when clustering became possible, when circulation achieved efficiency, When rain first fell on cooling basalt, somewhere in the gentle precipitation of a modern shower, molecules descend that participated in every phase of this planetary transformation. Their hydrogen and oxygen atoms preserve unchanged the elemental relationships that enabled the first molecular clustering, the first cloud formation, the first successful contact between liquid water and solid rock. The chemistry that once required extreme temperatures and pressures now operates in the moderate conditions that support forests, rivers, and the vast oceanic systems that regulate planetary climate. The water cycle continues its planetary breathing, inhaling moisture from oceanic surfaces warmed by gentle solar heating, exhaling precipitation through atmospheric cooling that occurs without the violent thermal gradients that characterized early Earth. Yet, the fundamental patterns remain unchanged. Water rises, cools, condenses, falls, flows, and rises again in cycles that preserve the geometric relationships between heating, cooling, and circulation established when the planet first achieved hydrological equilibrium. In the deepest ocean trenches, where pressure and temperature begin to approach the extreme conditions that characterized early Earth's surface, chemical processes continue to operate that echo the intensive weathering and mineral dissolution that first gave seawater its chemical complexity. The elements dissolved in modern seawater preserve the cumulative products of billions of years of chemical cycling that began when hot rain first extracted minerals from cooling volcanic rocks. Time moves towards silence. The rain falls with the same gentle persistence that enabled the emergence of biological complexity from purely chemical organization. Each drop carries the potential for continued planetary evolution while preserving the chemical and physical relationships that connect Earth's deep history with its continuing transformation. The water remembers, circulates, and waits patient as stone, persistent as gravity, endless as the planetary breathing that began when Earth first learned to balance fire with water in the cooling twilight of its youth. The ancient rain still falls. The circulation continues. The blue planet breathes with water, as it has breathed for billions of years, as it will breathe for billions more, carrying within its hydrological memory the complete story of planetary transformation from molten chaos to living world. The same rain that first fell on cooling stone now nourishes forests, fills rivers, and sustains the vast community of life that water itself made possible through patient circulation across the cooling face of Earth.